What if there existed particles that could never slow down, that were born already moving faster than light itself, and whose very existence would shatter everything we think we know about time, causality, and reality? Tonight we drift into the strange, unsolved corners of physics, where science ends and mystery begins. If the quiet hum of the universe helps you sleep, hit subscribe and let history and science carry you off every night. In the early years of the 20th century, a young patent clerk in Bern, Switzerland, was thinking about light, not in the way most people think about light, as something that illuminates a room or catches the dust floating in the air on a quiet afternoon, but in a far deeper, more unsettling way. He was asking what it would look like if you could chase a beam of light. What would you see if you ran alongside it, matching its speed exactly, keeping perfect pace with it through the darkness of space? The question sounds almost childlike in its simplicity, and yet it contained within it one of the most explosive ideas in the history of human thought. The young man's name was Albert Einstein, and the answer he eventually arrived at would not just change physics, it would change the very nature of reality as we understood it. The world Einstein inherited was a world of certainty. Isaac Newton had built a universe that ran like a clock. Space was fixed, absolute, unchanging, a vast and featureless stage upon which the drama of matter and energy played out. Time ticked forward at the same rate everywhere, for everyone, regardless of where they stood or how fast they moved. These were not assumptions people debated. They were the invisible architecture of reality, the foundational truths so obvious that questioning them would have seemed almost absurd. Mass was mass, distance was distance, time was time, and the universe in Newton's vision was a place of elegant, unwavering predictability. But cracks had already begun to appear in this beautiful clockwork, long before Einstein sat down to think about chasing light. In 1865, the Scottish physicist James Clerk Maxwell had published his extraordinary equations describing the behavior of electricity and magnetism. These four equations, among the most beautiful in all of science, showed that electric and magnetic fields were not separate phenomena, but two aspects of a single unified force. More than that, they predicted the existence of electromagnetic waves, and they gave a precise value for the speed at which those waves would travel. That value was approximately 299,792 kilometers per second. It was, Maxwell realized, the speed of light. Light was an electromagnetic wave, and it traveled at a very specific fixed speed. Here was the problem. In Newton's universe, speeds were relative. If you were standing still and the train passed you at 100 kilometers per hour, a passenger on that train throwing a ball at 50 kilometers per hour in the direction of travel would produce a ball moving at 150 kilometers per hour from your perspective, speeds added together cleanly and simply. This was called Galilean relativity, and it was so deeply intuitive that it barely needed to be stated. But Maxwell's equations did not behave this way. They gave a single fixed speed for light, not a speed relative to some observer, not a speed that could be added to or subtracted from depending on who was watching, but an absolute speed fixed and immovable. This was profoundly strange. In a Newtonian universe, nothing was supposed to have an absolute speed. Everything was relative to everything else. The physicists of the late 19th century tried to resolve this contradiction in what seemed like the most sensible way possible. They proposed that light, like sound, needed a medium to travel through. Sound travels through air, and its speed is measured relative to that air. Perhaps light traveled through some invisible, all-pervading substance that filled the cosmos, a substance they called the luminiferous ether. The speed of light that Maxwell's equations described would then be the speed of light relative to this ether, and as the Earth moved through the ether on its journey around the Sun, the speed of light, measured in different directions, should vary slightly, depending on whether you are moving with or against the ether wind. In 1887, two American physicists, Albert Michelson and Edward Morley designed an extraordinarily precise experiment to detect this ether wind. They split a beam of light, sent the two halves in perpendicular directions, and then recombined them, looking for tiny differences in the time it took each beam to complete its journey. If the ether existed, those differences should have been detectable. They found nothing, absolutely nothing. The speed of light appeared to be exactly the same in every direction, regardless of how the Earth was moving. The ether, if it existed at all, was producing no measurable effect. The experiment was repeated, refined, and repeated again. The answer was always the same: silence where there should have been signal. This was the landscape, confused, contradictory, and quietly desperate, into which Einstein arrived with his question about chasing a beam of light. His genius was not to look for a more complicated solution to the ether problem, but to ask what would happen if Maxwell was simply right. What if the speed of light really was constant, not relative to any medium, not relative to any observer, but genuinely absolutely constant for everyone everywhere under all circumstances? What if, instead of treating his as a paradox to be explained away, you accepted it as a fundamental truth of nature, and then asked what the universe would have to look like in order for it to be true? The answer he arrived at in 1905 was special relativity, and it was so strange that even today, more than a century later, it retains the power to make the mind reel. If the speed of light is the same for all observers, then space and time cannot be the fixed absolute things Newton had imagined. They must be flexible. They must bend and stretch depending on how fast you are moving. Two observers moving at different speeds will not agree on the length of a ruler, the rate of a clock, or even the order in which events occur. Time for a moving observer runs slower than time for a stationary one, a phenomenon called time dilation. Distances in the direction of motion contract, a phenomenon called length contraction. None of this is illusion. None of it is a trick of perception. It is the actual physical behavior of space and time, and at the heart of all of it, holding the entire structure together like a keystone, was the speed of light. The reason time had to slow down and space had to contract was precisely to ensure that every observer, regardless of their motion, would always measure light moving at exactly the same speed. The constancy of light's speed was not a consequence of special relativity. It was its foundation. The universe, Einstein was saying, was structured in such a way as to protect that constancy at all costs, even at the cost of our most cherished intuitions about space and time. From this foundation flowed one of the most famous equations in human history: E equals mA T, may T tree D D. Energy and mass, it turned out, were not separate things but different aspects of the same thing, interconvertible by a factor of the speed of light squared, a number so enormous that even a tiny amount, T of mass, contained a staggering amount of energy. This was not merely theoretical. It was the principle behind every nuclear reaction, every star burning in the night sky, every hydrogen bomb ever built. The universe at its most fundamental level ran on the convertibility of mass and energy, and the speed of light was the conversion factor. But special relativity did something else too, something that would haunt physicists for decades and eventually open the door to one of the strangest ideas in all of science. It established, with mathematical rigor, why nothing with mass could ever reach the speed of light. The argument was elegantly simple and utterly devastating. As an object moves faster, its kinetic energy increases. But in Einstein's universe, energy and mass are equivalent. So as an object gains kinetic energy, it also effectively gains mass. And as its mass increases, it becomes harder to accelerate. You need more energy to push it faster, but adding energy adds more mass, which requires more energy still. The faster you go, the harder it becomes to go faster. As you approach the speed of light, the amount of energy required to accelerate further approaches infinity. To actually reach the speed of light would require an infinite amount of energy. Since the universe does not have infinite energy to spare for the acceleration of any single object, the speed of light is, for anything with mass, an absolute and impassable barrier. This was the cosmic speed limit. It was not a rule imposed from outside, not a regulation written into the laws of physics by some external authority. It was a consequence, deep, inevitable, and inescapable, of the very structure of space-time itself. The universe was built in such a way that the speed of light served as an absolute boundary. Nothing could cross it. Nothing could even touch it. Anything with mass was forever confined, to the slower-than-light side of that boundary, doomed to approach it asymptotically, forever getting closer but never arriving. For most physicists, this was simply the end of the story. The speed of light was the limit. Objects with mass were trapped below it. End of discussion. But for a small number of thinkers, more mathematically adventurous, or perhaps just more willing to follow an equation wherever it led, regardless of how uncomfortable the destination, a question began to form. Einstein's equations described what happened as an object with mass approached the speed of light from below. The energy required went to infinity. The mass went to infinity. Time dilation and length contraction went to their most extreme values. But what, exactly, happened on the other side? The mathematics of special relativity did not simply break down at the speed of light and refuse to say anything beyond it. The equations continued. They did not stop at the boundary. They produced answers, strange answers, answers that seemed to describe something deeply paradoxical and perhaps deeply real. If you imagined an object that was already moving faster than light, already on the other side of the barrier, something curious happened. The mathematics did not produce infinities. Instead, it produced imaginary numbers, quantities involving the square root of -1, a mathematical entity that has no straightforward physical interpretation, but that appears throughout quantum mechanics and wave theory, and is therefore not automatically a sign of nonsense. The equations were saying something. They were saying that on the other side of the light barrier, there was a different kind of reality. Not a broken or impossible one, but simply a different one, governed by its own strange rules. The most unsettling of those rules had to do with time. In the familiar, slower-than-light world, time flows in one direction, cause precedes effect. The past is fixed and the future is open. This temporal arrow is so deeply embedded in our experience that it feels not like a feature of physics, but like a feature of existence itself. But for a hypothetical object moving faster than light, the mathematics suggested something else entirely. Such an object, moving between 2 points in space-time, could in principle arrive before it departed, from the perspective of certain observers. The direction of time for such an object was not fixed in the way it was for us. Causality, the bedrock principle that causes always precede their effects, would be in danger of unraveling. This was not a small problem. This was not a small problem. Causality is not just one principle among many in physics. It is the principle upon which all of science, and indeed all of coherent thought, depends. If effects can precede causes, if information can travel backward through time, then the entire logical structure of the universe becomes unstable. Paradoxes proliferate. A signal sent faster than light could, under the right circumstances, be received before it was sent. An event could cause its own non-occurrence. The universe could become a place of self-contradictory loops and logical impossibilities. For many physicists, this alone was sufficient reason to dismiss faster-than-light travel as not merely physically impossible, but conceptually incoherent. And yet the equations sat there, patient and undeniable, hinting at something on the other side. The mathematics did not know it was supposed to be impossible. It simply described what it described, and what it described, and what it described, in outline, if not in detail, was a universe with two distinct realms, the slower-than-light realm of ordinary matter and experience, and a faster-than-light realm of something else, something that obeyed the same fundamental equations but lived in A mirror world where the rules were inverted, where imaginary numbers replaced real ones, where the relationship between energy and velocity ran in the opposite direction. In the slower-than-light world, to accelerate an object with mass requires energy, and the closer you get to the speed of light, the more energy you need. In the hypothetical, faster-than-light world, the relationship is reversed. The faster such an object moves, the less energy it has. To slow it down, you would need to add energy, and the ultimate resting state for such an object, if slowing to the speed of light requires infinite energy, would be a particle that can never be slowed to the speed of light at all. Just as ordinary matter can approach but never reach the light barrier from below, a faster-than-light particle could approach but never reach the light barrier from above. The speed of light would be not just a ceiling for ordinary matter, but a floor for this strange other kind of matter. This was the mathematical landscape that waited, quiet and unexplored, in the margins of Einstein's equations for the first half of the 20th century. Nobody had named what lived in that landscape. Nobody had seriously proposed that the mathematics described anything real. It was the kind of theoretical curiosity that physicists note and file away. Interesting, perhaps, but almost certainly not physical. Almost certainly not something the universe had actually bothered to make. Almost certainly, but not certainly. And in science, that difference is everything. The universe has a long and humbling history of making things that seemed too strange to be real. It made black holes, which relativity predicted and physicists resisted for decades before the evidence became undeniable. It made quantum superposition, in which particles exist in multiple states simultaneously until observed. It made antimatter, predicted by Paul Dirac's equations before anyone had seen so much as a trace of it in nature. Again and again, the universe had looked at the strangest, most counterintuitive corners of its own mathematical description and said, yes, this too, this also. The question in 1967 was whether it had done so again, whether on the far side of Einstein's Great Barrier, in the imaginary number realm that the equations gestured toward, but did not fully illuminate, there was something real, something with properties, something that could, at least in principle, be detected, studied, and understood. A particle that was not slowed by the speed of light, but defined by it. A particle that lived not below the barrier but above it, permanently, inescapably, and with consequences for everything we thought we knew about time, causality, and the deep structure of the cosmos. That particle had not yet been named, but it was coming, and when it arrived, it would bring with it one of the most fascinating, frustrating, and enduringly strange chapters in the history of physics. The universe, it turned out, had more to say. It always does. Standing at the edge of the known and staring out into the dark, you begin to understand that the barrier Einstein found was not a wall built to keep us in. It was a door, slightly ajar, with something on the other side that the universe has not yet decided whether to show us. The speed of light was never just a limit. It was always also a threshold. There is a particular kind of courage required to take an equation seriously, not the courage of the laboratory, where experiments fail and equipment breaks, and years of work can be undone by a single contaminated sample. Not even the courage of the lecture hall, where ideas are challenged and reputations are staked on arguments that may not hold, but the quieter, stranger courage of sitting alone with a piece of mathematics and asking, with complete sincerity, whether what it is describing might actually be real, whether the universe in its vast and indifferent creativity might have bothered to make the thing the numbers are pointing at. This is the courage that separates the merely competent physicist from the genuinely visionary one. And in 1967, a young Columbia University physicist named Gerald Feinberg displayed it in full. Feinberg was not working in isolation from the history of the problem. The mathematical possibility of faster-than-light particles had been gestured at before. In scattered papers and theoretical asides, by physicists who noticed the structure of Einstein's equations and what they implied beyond the light barrier. The German physicist Arnold Sommerfeld had touched on the idea as early as 1904, before special relativity was even fully formulated. Others had noted it and moved on, treating it as a mathematical curiosity rather than a physical proposal. The equations allowed for something on the other side of the light barrier, yes, but allowing and existing are very different things. And most physicists were content to leave the question unanswered, the door unopened. What Feinberg did was different. He did not merely note the mathematical possibility and file it away. He took it seriously as a physical hypothesis. He asked not just whether the mathematics permitted faster than light particles, but what those particles would actually be like, what properties they would have, how they would behave, what rules would govern them, and crucially, whether there was any reason in principle why they could not exist. He wrote up his analysis and published it in the prestigious journal, Physical Review, and in doing so he gave the idea something it had never had before, a name, a framework, and a legitimate place in the scientific conversation. He called them tachy. The name came from the Greek word tachys, meaning swift. It was an elegant and appropriate choice. Simple, evocative, carrying within it the essential character of the thing being described without overclaiming or sensationalizing. Tachyons were swift, more than swift. They were particles for whom the speed of light was not a ceiling to strain against, but a floor they could never descend to. A lower boundary as absolute and impassable for them as it was an upper boundary for everything else. In the taxonomy of motion that special relativity implied, Feinberg recognized three distinct classes of object. There were the Tachyons, ordinary matter, particles with real positive mass, forever confined to speeds below the speed of light. There were the Luxons, particles like photons, massless particles that traveled at exactly the speed of light and could do nothing else. And then there were the Tachyons, particles with a very strange kind of mass indeed, particles that existed entirely above the light barrier and could never come below it. The mass of a tachyon, in Feinberg's framework, was what mathematicians call an imaginary number, a multiple of the square root of -1. In everyday language, imaginary numbers sound like a polite way of saying not real, a mathematical fiction with no counterpart in the physical world. But this intuition is misleading. Imaginary numbers are not imaginary in the sense of being invented or pretend. They are a genuine and indispensable part of mathematics, appearing throughout quantum mechanics, electrical engineering, fluid dynamics, and signal processing. They are tools that describe real phenomena all the time. The wave functions of quantum mechanics are complex numbers, combining real and imaginary parts, and they describe the most precisely verified predictions in the history of science. The appearance of an imaginary mass in the mathematics of tachyons was strange, certainly, but it was not automatically a sign that the concept was nonsense. What imaginary mass meant physically was the real question, and Feinberg worked through it carefully. In the familiar world of Tachyons, mass is the resistance to acceleration. The heavier something is, the harder it is to speed up or slow down. Energy and velocity are related in a specific way. As velocity increases toward the speed of light, the energy required increases without bound, running off toward infinity at the barrier. For tachyons, with their imaginary mass, this relationship was inverted in a deeply peculiar way. As a tachyon slowed down, as its speed decreased toward the speed of light from above, its energy increased, and as a tachyon moved faster and faster, its energy decreased. The most energetic state of a tachyon was the slowest one it could occupy, moving just barely faster than light. The least energetic state, the ground state, the state a tachyon would naturally fall into if it lost energy, was one of infinite speed. This inversion of the energy-velocity relationship was one of the most conceptually jarring features of Feinberg's proposal. We are accustomed to a world in which more energy means more speed. a faster bullet, a faster rocket, a faster particle in an accelerator. All of these require more energy than their slower counterparts. The universe of tachyons ran on a different logic. In that universe, giving a tachyon energy slowed it down. Taking energy away sped it up. A tachyon radiating energy, losing it to its surroundings, would accelerate. An infinitely fast tachyon would be a tachyon with no energy at all, a strange and paradoxical ground state that seems to dissolve into pure motion divorced from any energetic content. The implications of this energy velocity inversion extended into thermodynamics in ways that were deeply unsettling. In ordinary thermodynamics, systems tend to lose energy and settle into their lowest energy states. A warm object radiates heat and cools down. A vibrating string loses energy and comes to rest. This tendency toward lower energy is one of the most universal features of physical systems. If tachyons obeyed the same tendency, and there was no obvious reason why they should not, then they would tend to accelerate over time, radiating energy and moving faster and faster until they reached infinite speed. The universe, if it contained tachyons, might be full of particles in the process of accelerating to infinity, or already there, moving at speeds so far beyond light that the concept of speed itself begins to lose its meaning. Feinberg was aware of these difficulties. He was also aware of a much larger and more fundamental problem, one that had discouraged physicists from taking faster-than-light particles seriously for decades. This was the problem of causality, the principle that causes must always precede their effects, that information cannot travel backward in time, that the logical order of events is fixed and cannot be inverted by any physical process. In special relativity, the relationship between faster-than-light travel and time reversal is not merely speculative. It is a direct mathematical consequence of the structure of space-time. A signal traveling faster than light between two events will, from the perspective of some observers in relative motion, appear to travel backward in time. This is not an optical illusion or a perspective trick. It is a genuine feature of how space-time geometry works when the invariant speed limit of light is exceeded. The causality problem had been the great wall blocking serious consideration of faster-than-light physics for as long as special relativity had existed. If tachyons carry information, and if that information could arrive before it was sent, then the universe became a place of logical paradoxes. You could, in principle, send a message to your past self. You could receive the answer to a question before you asked it. You could create causal loops in which an event caused itself, or prevented itself, or both. The universe would become not just strange but incoherent, a place where the very concepts of before and after, cause and effect, lost their meaning. Feinberg did not dismiss this problem, but he did argue, carefully and in detail, that it was not necessarily fatal to the tachyon hypothesis. The key question was not whether tachyons traveled faster than light. By definition they did, but whether they could be used to transmit information. If tachyons existed but could not be controlled, could not be produced at will and directed to carry a specific message, then the causality paradoxes would never arise in practice. A tachyon that happened to be emitted by some natural process and happened to arrive somewhere before the light from that process was not the same thing as a tachyon carrying a deliberate signal backward in time. The difference was control, and Feinberg argued that there were reasons to think tachyons, even if they existed, might be fundamentally uncontrollable, that the same quantum mechanical principles that governed all particle interactions might make it impossible to use tachyons as a signaling medium, even in principle. This argument drew on a broader principle that had been articulated in various forms by different physicists, the idea that the universe seemed to conspire, through its fundamental laws, to protect causality. Whenever a theoretical possibility for faster-than-light signaling appeared in the mathematics, some other feature of the theory always seemed to close the door. In quantum field theory, A mathematical property called microcausality ensured that measurements made at space-like separated points that could only be connected by a faster-than-light signal, could not influence each other. The theory seemed to have causality protection built in at a deep level, not as an added constraint but as an emergent consequence of its structure. Feinberg's proposal existed in productive tension with these protections. He was not claiming that tachyons could be used to send messages through time. He was claiming something more subtle, that particles with imaginary mass and faster-than-light velocities might exist as genuine physical entities without necessarily violating causality in any practical or paradoxical way. Whether the universe actually contained such particles was an empirical question, not a logical one. The mathematics did not forbid them. The known laws of physics did not definitively rule them out. The question of whether they existed was, ultimately, a question for experiment. What would tachyons actually look like in nature if they existed? How would they interact with ordinary matter? How would they be produced? And how could they be detected? These were the questions that followed naturally from Feinberg's theoretical proposal, and they were questions without easy answers. Tachyons, by virtue of their faster-than-light nature, would not interact with ordinary matter in any of the familiar ways. They could not be stopped by a detector in the conventional sense, since stopping them would require reducing their speed to the speed of light, which would require infinite energy. Any interaction a tachyon had with ordinary matter would be an interaction between two fundamentally different sectors of reality, connected only by the exchange of energy and whatever quantum numbers the tachyon carried. One approach to detecting tachyons focused on the phenomenon of Cherenkov radiation. When a charged particle moves through a medium at a speed greater than the speed of light in that medium, not the universal speed of light in that medium, not the universal speed of light in vacuum, but the reduced speed of light in glass or water or some other material, it emits a characteristic cone of radiation, a kind of optical shock wave analogous to the sonic boom produced by a supersonic aircraft. This is Cherenkov radiation, and it is routinely observed in nuclear reactors, where the blue glow around the reactor core is a visible manifestation of it. If tachyons were charged and moved through the vacuum faster than the speed of light in vacuum, they might emit a similar radiation, a vacuum Cherenkov radiation that could in principle be detected. Searches for this signature were proposed and in some cases carried out without success. Other approaches to tachyon detection focused on the way they might appear in particle physics experiments. In high-energy collisions, particles are created from the energy of the collision, constrained by conservation laws. If tachyons existed and could be produced in such collisions, they might leave characteristic signatures, missing energy, anomalous momentum distributions, unusual patterns of particle production that could not be explained by known physics. The absence of any such signatures in decades of particle physics experiments was not definitive proof that tachyons did not exist. They might be produced too rarely, or interact too weakly, or leave signatures too subtle to distinguish from background noise, but it was not encouraging. There was also a deeper theoretical problem that emerged in the years after Feinberg's paper, one that cut to the heart of the tachyon concept in quantum field theory. When physicists tried to build a fully consistent quantum field theory containing tachyons, a theory that respected the principles of quantum mechanics, special relativity, and the requirements of mathematical consistency, they found something troubling. A field whose particles had imaginary mass was not simply a field with unusual particles. It was an unstable field. It was a field sitting at the top of a potential energy hill, poised to roll down into a different configuration. In the language of quantum field theory, imaginary mass signaled not a new type of particle, but a new type of instability, a sign that the vacuum of the theory was not in its true ground state. This reinterpretation of imaginary mass as instability, rather than as a new particle species, had profound implications. It meant that tachyons in quantum field theory were not stable, persistent particles that flew through the universe at faster than light speeds. They were instead transient disturbances associated with a field undergoing a phase transition, settling from an unstable false vacuum into a stable true vacuum. The tachyon was not a thing that existed. It was a signal that something was about to change. This was not an entirely unfamiliar idea. The Higgs field, before the electro-weak symmetry breaking that occurred in the early universe and gave particles their mass, was itself described by equations that looked like a tachyonic field. The Higgs boson, in a very precise mathematical sense, began its life as a tachyon. The symmetry breaking that stabilized it, the rolling of the potential from an unstabilized to a stable minimum, was the event that populated the universe with massive particles. The tachyon, in this view, was not a visitor from a faster-than-light realm but a harbinger of cosmic change. In string theory, tachyons played a similar and somewhat notorious role. The earliest versions of string theory, the bosonic string theory developed in the late 1960s and early 1970s, contained a tachyonic mode in their spectrum. This was widely regarded as a serious problem, a sign that the theory was sitting in an unstable vacuum, and was therefore not a viable description of physical reality. Much of the subsequent development of string theory was driven in part by the need to eliminate or explain this tachyonic mode. Superstring theory, which incorporated supersymmetry, removed the tachyon from the spectrum, and was for this reason considered a significant advance. In more recent work, physicists like Ashok Sen have studied tachyonic condensation, the process by which a tachyonic field rolls to its stable minimum, as a way of understanding how unstable configurations of strings decay into stable ones. The tachyon, in this context, was not a particle to be detected, but a mathematical tool for understanding stability and phase transitions in string theory. And yet, through all of this theoretical development, through all the reinterpretations and reformulations and the gradual absorption of the tachyon concept into the deeper structures of quantum field theory and string theory, the original question that Feinberg asked never quite went away. Was there, somewhere in the universe, a particle that genuinely moved faster than light? Not a mathematical instability, not a harbinger of phase transitions, not a tool of theoretical analysis, but an actual physical entity moving through space at a speed that exceeded the cosmic speed limit, living in the inverted world on the other side of Einstein's barrier. The theoretical arguments against it had grown more sophisticated and in some ways more persuasive over the decades. The experimental searches had come up empty. The concept had been transformed and reinterpreted until it barely resembled Feinberg's original proposal. But the universe has never been particularly respectful of theoretical expectations. It has made things that were theoretically problematic and experimentally unexpected more times than any physicist would be comfortable counting. It made pulsars and quasars, and the cosmic microwave background, and the accelerating expansion of the universe, none of which were predicted with any confidence before they were found. It continues to produce surprises at every scale, from the quantum to the cosmological, each one a reminder that the map is not the territory, and the equations are not the universe. Gerald Feinberg sat down in 1967 with some equations, and the courage to take them seriously, and he opened a door that has never been fully closed. The tachyon may not be what he thought it was. It may not be what anyone thinks it is, but the question it represents, the question of what lives on the other side of the light barrier, in the strange, inverted world that Einstein's mathematics gestures toward, remains one of the most quietly persistent mysteries in all of physics. What is out there, past the speed of light, in the part of the universe our instruments cannot see and our particles cannot reach? The equations have always had an answer. We just have not yet learned how to read it. The tachyon was never just a particle. It was always a question the universe was asking back. Time is the most intimate fact of human existence. It is more fundamental to our experience than color, or sound, or the feeling of solid ground beneath our feet. We are embedded in it so completely, so thoroughly, so without any possibility of distance or perspective, that we rarely think to question it at all. It moves, we say, forward, always forward, from the past that is fixed and gone into the future that is open and unwritten. This movement feels not like a feature of the universe that might have been otherwise, but like the very condition of existence itself. To be alive is to move through me. To think is to remember a past and anticipate a future. The arrow of time, that relentless, one-directional flow from before to after, is so deeply embedded in our consciousness that imagining its absence requires an almost violent act of mental effort. And yet the arrow of time is one of the deepest and most genuinely unsolved problems in all of physics. It is a problem that sits at the intersection of thermodynamics, cosmology, quantum mechanics, and the philosophy of causality, touching each of these fields without being fully resolved by any of them. The fundamental equations of physics, Newton's laws, Maxwell's equations, Einstein's relativity, the Schrödinger equation of quantum mechanics, are almost entirely time-symmetric. They work equally well in both directions. If you filmed a collision between two billiard balls and played the film backward, the reversed collision would look perfectly natural, perfectly consistent with the laws of physics. The laws do not care which direction time runs. They are indifferent to the arrow, and yet the arrow is there, unmistakably, irreversibly, written into every aspect of our experience. Ice melts but does not spontaneously refreeze. Smoke disperses but does not gather itself back into a flame. The dead do not return to life. Something is breaking the symmetry of the fundamental equations and imposing a direction on time, and physicists have been arguing about what that something is for well over a century. Into this already fraught landscape, tachyons arrive like a lit match dropped into a room full of dry paper. Because if tachyons exist, if there are genuine physical particles that move faster than light, then the problem of time's arrow does not merely become more complicated. It becomes potentially catastrophic. The arrow of time does not just waver or bend in the presence of tachyons. It risks being broken entirely, shattered into pieces, leaving behind not an arrow pointing in one direction, but a tangle of temporal loops in which the distinction between before and after dissolves into incoherence. To understand why, it is necessary to understand something about the geometry of space-time that special relativity revealed. Before Einstein, space and time were separate things. Space was the three-dimensional arena in which events occurred, and time was the independent variable that told you when they occurred. They were related, certainly. To describe an event, you needed both a where and a when, but they were fundamentally different kinds of thing, measured in different units, obeying different rules. Einstein's great insight was that this separation was an illusion, or rather, that it was a perspective-dependent feature of reality, rather than an absolute one. Space and time were not two separate things, but two aspects of a single four-dimensional continuum. Space-time. In this four-dimensional space-time, the relationship between two events, 2 points in the continuum, was described by something called the space-time interval. This interval combined the spatial distance and the temporal separation between the events into a single quantity that all observers, regardless of their motion, would agree on. It was the invariant quantity of special relativity, the thing that was the same for everyone even as individual measurements of space and time varied. And depending on the value of this interval, the relationship between two events fell into one of three categories, each with profound implications for causality and the possibility of faster-than-light travel. If the space-time interval between two events was positive, if the temporal separation was large enough relative to the spatial distance that even light could not bridge the gap in the available time, the events we said to be time-like separated. For time-like separated events, there was no ambiguity about which came first. Every observer in every state of motion would agree on the temporal order. Event A happened before event B, and that ordering was fixed, absolute, and universal. The arrow of time was secure. Nothing that happened at event A could have any effect on event B, unless it traveled slower than light. But for all the things that did travel slower than light, the causal relationship was unambiguous. This was the safe zone of causality, the region of space-time where the arrow pointed clearly and nothing moved backward. If the space-time interval was zero, if the events were separated by exactly the distance that light would travel and exactly the available time, the events were said to be light-like separated, connected by the path of a light beam. Light, traveling at its fixed and invariant speed, connected the two events, and again the temporal order was fixed for all observers. The arrow held, but if the space-time interval was negative, if the spatial separation was so large and the temporal separation so small that not even light could bridge the gap, the events were said to be space-like separated, and here everything changed. For space-like separated events, there was no fixed temporal order. Different observers in different states of motion would disagree about which event came first. One observer might say, event A preceded event B. Another observer moving at a different velocity would say, event B preceded event A. A third observer might say they were simultaneous. All of these observers would be equally correct. The temporal ordering of space-like separated events was not a fixed feature of reality, but a perspective-dependent one, varying with the observer's state of motion. For ordinary matter, moving slower than light, this relativity of temporal ordering F, or space-like separated events, was a curious feature of space-time geometry, but not a practical problem. Ordinary matter could not connect two space-like separated events, could not travel from one to the other because doing so would require exceeding the speed of light. The events were, in a very precise sense, causally disconnected. Nothing that happened at event A could influence event B if the two events were space-like separated, because no signal, no particle, no influence of any kind could travel fast enough to bridge the gap. The relativity of their temporal ordering was irrelevant to causality because causality, for slower-than-light physics, never needed to connect them. Tachyons destroyed this comfortable situation completely. A tachyon, moving faster than light, could connect two space-like separated events. It could travel from event A to event B even when they were space-like separated, even when their temporal ordering was relative and observer-dependent. And here was the catastrophe. Because the temporal ordering of space-like separated events depended on the observer's velocity, what appeared to one observer as a tachyon, emitted at event A and absorbed at event B, would appear to another observer, moving at a different velocity, as a tachyon emitted at event B and absorbed at event A. The same physical process, the same tachyon, would be seen by one observer as traveling forward in time and by another observer as traveling backward in time. This was not a subtle or technical point. It was a direct, unavoidable consequence of the geometry of space-time, requiring no assumptions beyond the ones already built into special relativity. If tachyons could travel between space-like separated events, and if the temporal ordering of those events was observer-dependent, then there was no observer-independent fact about whether the tachyon was moving forward or backward in time. The direction of its temporal travel was relative, just like the ordering of the events it connected. And this meant that in some reference frames, tachyons genuinely traveled backward in time. Not apparently, not from a limited perspective, but actually, physically, in the only sense that mattered in a relativistic universe, where there was no absolute time against which to measure. The implications for causality were immediate and devastating. Consider a simple thought experiment that physicists called the tachyonic antitelephone, a name that captured its paradoxical character with dark precision. Imagine two observers, Alice and Bob, moving at different velocities relative to each other, separated by a large distance. Alice emits a tachyon that travels, in her reference frame, forward in time and across the space to Bob. Bob receives the tachyon, and using his own tachyon emitter, sends a tachyon back to Alice. In Bob's reference frame, both of these tachyon journeys move forward in time, but because of the relativity of simultaneity for space-like separated events, the combination of the two journeys, from Alice to Bob and back, could result in the return tachyon arriving at Alice's location before Alice sent the original one. Alice could receive a reply before she asked the question. An effect could precede its cause. The most fundamental logical structure of reality, the principle that causes come before effects, would be violated. This was not a flaw in the thought experiment. It was not a case of sloppy reasoning or hidden assumptions. The tachyonic antitelephone was a rigorous consequence of combining faster-than-light travel with the kinematics of special relativity, and numerous physicists had worked through it carefully, from different angles with the same result. If tachyons existed and could be used to send signals, causality was not merely threatened. It was demolished. The universe would become a place where you could, in principle, receive information from your own future, use that information to make decisions that changed what your future self sent, and thereby create loops of self-referential causality that had no consistent solution. The grandfather paradox, the famous puzzle of traveling back in time to prevent your own birth, had a tachyonic analog that was just as vicious and just as insoluble. Physicists who wanted to preserve the possibility of tachyons without sacrificing causality were forced to look for ways out of this predicament, and several were proposed with varying degrees of persuasiveness. One approach was the reinterpretation principle, sometimes called the Feinberg-Sudarshan reinterpretation principle after the physicists who explored it most carefully. This principle proposed that what appeared in one reference frame as a tachyon traveling backward in time should be reinterpreted in that frame as a tachyon of negative energy traveling forward in time. In quantum mechanics, negative energy particles were already a familiar concept. They were the basis of antimatter, with Dirac's antiparticles understood as ordinary particles moving backward in time, or equivalently, as positive energy particles moving forward in time. The reinterpretation principle extended this idea to tachyons, arguing that the apparent time reversal was an artifact of perspective, and that a consistent description could always be constructed in which all tachyons moved forward in time, some with positive energy, and some with negative energy. The problem with this approach was that it did not actually solve the causality problem, it reframed it. The tachyonic antitelephone argument still worked even with the reinterpretation principle applied consistently. What changed was the description, not the CS. The apparent backward-in-time tachyon became a forward-in-time tachyon with negative energy. But the causal loop, the ability to influence your own past, persisted. Renaming the paradox did not make it go away. Another approach to the causality problem was more radical and more interesting. Some physicists argued that the universe itself contained a mechanism for preventing causal paradoxes, not just for tachyons but for any hypothetical time travel scenario. This was Stephen Hawking's chronology protection conjecture, proposed in 1992, which argued that the laws of physics conspired, through quantum effects, to prevent the formation of closed time-like curves, paths through space-time that looped back to their own starting point. Hawking did not prove this conjecture rigorously, and it remains unproven today. But there was suggestive evidence that quantum vacuum fluctuations would grow without bound in any space-time geometry that permitted time travel, effectively destroying the geometry before the time loop could be completed. The universe, in this view, was self-protecting, not through any special law added to prevent paradoxes, but through the ordinary operation of quantum physics and extreme space-time geometries. If some version of chronology protection was correct, then tachyons could not be used to create causal paradoxes, not because they did not travel faster than light, but because any attempt to arrange them into a causal loop would be disrupted by quantum effects before the loop could close. The arrow of time would be protected not by fiat but by physics. This was a more satisfying resolution than simply asserting that tachyons could not be controlled, but it came with its own costs. It required the quantum theory of gravity to behave in specific ways that had not been established, and might not be true. The deeper question that tachyons forced upon physics was not merely whether causality could be protected, but why causality existed at all. The fundamental equations of physics, as noted before, were time-symmetric. The arrow of time in our everyday experience was generally attributed to thermodynamics, specifically to the second law, which stated that entropy, the measure of disorder in a system, always increased over time. The reason ice melted and smoke dispersed and the dead stayed dead was that the disordered states were overwhelmingly more probable than the ordered ones, and systems left to themselves would almost always evolve from order toward disorder, from low entropy toward high entropy, simply because there were vastly more high entropy states than low entropy ones. The arrow of time was, on this view, a statistical phenomenon, not a fundamental law but an overwhelmingly probable tendency. This statistical origin of the arrow of time was both its strength and its vulnerability. Its strength was that it explained the observed asymmetry between past and future without requiring any time asymmetric, fundamental law. Its vulnerability was that it made the arrow contingent, dependent on the initial conditions of the universe, rather than on any deep principle. The early universe happened to be in an extremely low entropy state, and everything since has been the long, slow, inexorable relaxation from that initial improbability toward equilibrium. The arrow of time, in this picture, was not a feature of the laws but a feature of the initial conditions. In a universe that had started in a high entropy state, or in a universe that had been running forever with no special initial conditions, the arrow might not exist at all, or might point in different directions in different regions. Tachyons complicated this picture in multiple ways. If tachyons existed and naturally accelerated toward higher speeds as they low, Saint energy, as the inverted energy-velocity relationship suggested they might, then they represented a systematic tendency in the universe that ran counter to the usual thermodynamic arrow. Ordinary matter lost energy and slowed down. Tachyons lost energy and sped up, eventually reaching infinite speed and dissolving into a kind of energyless pure motion. The question of how tachyonic thermodynamics interacted with ordinary thermodynamics, and whether the combined system had a well-defined arrow of time, was one that physicists had barely begun to explore. There was also a more subtle and more disturbing possibility that the existence of tachyons raised for the nature of time. In standard physics, even with the relativistic relativity of simultaneity for space-like separated events, there was a clear causal structure to space-time. Events in the past light cone of any given event were the ones that could have influenced it. Events in the future light cone were the ones it could influence. Events in the space-like region, outside both light cones, were causally disconnected. This causal structure, defined by the light cones, was the backbone of relativistic physics. It was what allowed the theory to be consistent even while giving up on absolute simultaneity. The light cones were the fixed scaffolding on which the flexible observer-dependent rest of space-time geometry hung. Tachyons, connecting events that lay in each other's space-like regions, reached outside the light cones. They did not merely bend the causal structure of space-time, they punctured it. In a universe with tachyons, the neat separation of space-time into past light cone, future light cone, and causally disconnected space-like region broke down. Every event was potentially connected to every other event, regardless of their separation, because a sufficiently energetic tachyon could bridge any spatial stance in any time interval, however small. The causal structure that underpinned all of relativistic physics The structure that made the theory coherent and consistent was threatened at its foundations. What would it actually feel like to live in a universe where the arrow of time had become a circle, where cause and effect were not a sequence, but a loop? The question sounds philosophical, but it had physical content. A universe with closed causal loops was not just strange, it was potentially self-contradictory in a way that made prediction impossible. In ordinary physics, even probabilistic quantum physics, the future was open. You could not predict it with certainty, but you could assign probabilities. The laws of physics, given the present state of a system, told you the range of possible futures and their likelihoods. In a universe with closed causal loops, this forward-directed predictive structure collapsed. The present was not just influenced by the past but also by the future, because information could circle back. The state of a system at any given moment was constrained not just by its history, but by its own future effects on itself. Prediction became not just difficult but conceptually undefined. The universe would have to be self-consistent in a much stronger sense than we were accustomed to, not just obeying the laws of physics at each moment but satisfying a global consistency condition that linked every event to every other through the web of causal loops. Some physicists found this prospect not horrifying but fascinating. The universe as a self-consistent whole, every event constrained by its relationships with every other event across all of time. There was a kind of austere beauty to it. It resonated with certain interpretations of quantum mechanics, particularly the sum over histories approach developed by Richard Feynman, in which the behavior of a particle was determined not by its trajectory through time, but by the interference of all possible histories simultaneously. It resonated with the block universe interpretation of general relativity, in which past, present, and future all existed simultaneously in a four-dimensional space-time block, and the apparent flow of time was an illusion generated by the way conscious observers were embedded in the block. In these frameworks, time was already less arrow-like than it appeared, already more circular, already more a feature of perspective than of physics. The tachyon sat at the center of all of this, a single hypothetical particle carrying within its imaginary mass and faster-than-light velocity the seeds of the deepest questions in physics. It was not just a fast particle, it was a challenge to everything we thought we understood about time. Its direction, its asymmetry, its role as the medium through which causality operated, its status as the most fundamental and intimate fact of our existence, whether tachyons existed or not. The questions they forced upon physics were real and profound and unresolved. The arrow of time pointed forward. We knew that much, but why it pointed forward? What prevented it from bending? What would happen if something could make it curve back on itself? These remained open questions, written in the same language of mathematics and mystery that had always defined the frontier of human understanding. Time, it turns out, is not a river with one mouth. It is an ocean with no shore. There is a particular kind of frustration that belongs exclusively to the search for something that might not exist. It is different from the frustration of searching for something you know is there. A lost key, a misplaced document, a signal buried in noise, where the search has a guaranteed end and failure is merely a temporary condition. The frustration of searching for something that might not exist is quieter, more philosophical, and in some ways more corrosive. Every negative result is ambiguous. Every empty detector, every blank data set, every empty detector, every blank data set, every experiment that returns nothing could mean one of two entirely different things. Either the thing is not there, or the thing is there, but you are not looking in the right way, with the right tools at the right scale, in the right corner of the universe. The absence of evidence, as the saying goes, is not evidence of absence. But it is not nothing either. It accumulates. It weighs on the hypothesis, and in the case of tachyons, it has been accumulating for more than half a century without resolution. The search for tachyons did not begin immediately after Gerald Feinberg's 1967 paper. Science moves at its own pace, and theoretical proposals, however interesting, must compete for experimental attention with a vast array of other priorities. The late 1960s and early 1970s were years of extraordinary productivity in particle physics, with the development of the Standard Model, the discovery of quarks, and the unification of the electromagnetic and weak forces, all demanding experimental attention and resources. Tachyons, as hypothetical particles with imaginary mass and no guaranteed interaction with ordinary matter, were not at the top of anyone's experimental agenda. But gradually, as the theoretical framework matured, and as physicists began to think carefully about what signatures tachyons might leave in existing data or in dedicated experiments, searches began to be proposed and eventually carried out. The first and most immediate problem facing any tachyon search was the absence of a well-defined theory of how tachyons would interact with ordinary matter. In particle physics, detecting a particle requires that it interact with your detector in some way. It must leave a track, deposit energy, trigger a signal of some kind. The entire experimental program of modern particle physics is built on the premise that particles interact and that those interactions leave measurable traces. For ordinary particles, the Standard Model provided precise predictions for interaction rates, cross-sections, and decay products that experimenters could test against. For tachyons, no such theory existed. Feinberg had described their kinematic properties, their energy-velocity relationship, their imaginary mass, their faster-than-light motion, but the question of how they coupled to ordinary particles, how they were produced, how they were absorbed, was left almost entirely open. Without a theory of tachyon interactions, designing an experiment to detect them was like designing a net without knowing the size, shape, or behavior of the fish you were trying to catch. One approach that did not require detailed knowledge of tachyon interactions was the search for the kinematic signatures that tachyons would necessarily leave if they were produced in particle collisions. In any high-energy collision, energy and momentum must be conserved. If a tachyon were produced in such a collision and escaped the detector without being absorbed, which, given their hypothetical weak interactions, seemed plausible, it would carry away energy and momentum that would appear to be missing from the event. This missing energy signature was already a powerful tool in particle physics, famously used in the discovery of the neutrino, and later in the search for supersymmetric particles and dark matter candidates. The idea was to look for events in which the visible products of a collision did not balance, in which the books did not add up, and attribute the discrepancy to the invisible departure of a tachyon. The difficulty was that missing energy signatures were not unique to tachyons. Neutrinos produced the same signature, and neutrinos were known to exist in enormous numbers. Any new weakly interacting particle would produce missing energy. The challenge was not detecting missing energy. That was routine, but distinguishing tachyonic missing energy from the missing energy produced by neutrinos and other known particles. This required either a distinctive additional signature that tachyons would produce and neutrinos would not, or a statistical analysis of missing energy distributions that might reveal the presence of an additional invisible particle species. Neither approach was straightforward, and the searches that were conducted in the 1970s and 1980s did not find any evidence for tachyons in the missing energy distributions of particle collision events. A more targeted experimental approach focused on the specific kinematic properties of tachyons. One distinctive feature of a faster-than-light particle was that its velocity was always greater than the speed of light, which meant that in any reference frame, it would travel faster than light could travel the same distance. If a tachyon were produced in a localized event, say, a nuclear reaction or a particle collision, it would arrive at a distant detector before light from the same event could arrive. This superluminal arrival time was, in principle, a clean and unambiguous signature. You would see the signal in your detector before you received the light from the source. No known particle or physical process could produce this signature. Detecting it would be, without any possibility of misinterpretation, evidence of faster-than-light travel. Several experiments in the 1970s and 1980s looked for this superluminal arrival signature in cosmic ray events. Cosmic rays, high-energy particles arriving from space and colliding with the upper atmosphere, produced cascades of secondary particles that rained down on detectors at the Earth's surface. If tachyons were produced in these cascades, they might arrive at surface detectors before the main body of the cascade, producing early arrival signals that preceded the expected timing by more than any known particle could account for. Detectors were set up to look for these early arrivals, and the data were carefully analyzed. Nothing was found. The timing of cosmic ray arrival patterns was consistent with known physics and showed no evidence of superluminal particles arriving ahead of the cascade. Searches for tachyons were also conducted in the context of radioactive decay. Some physicists have proposed that if neutrinos had imaginary mass, if they were, in the technical sense, tachyonic, this would be revealed in the energy spectrum of electrons emitted in beta decay. In ordinary beta decay, a neutron decays into a proton, an electron, and an antineutrino, with the available energy distributed among the three products, according to the laws of kinematics. The shape of the electron energy spectrum near its maximum value, near the endpoint of the spectrum, where the electron carried away nearly all the available energy, was sensitive to the mass of the neutrino. For a neutrino with real positive mass, the spectrum would approach the endpoint in a specific way. For a neutrino with imagina, mass a tachyonic neutrino, the approach to the endpoint would be different, producing a distinctive shape that could, in principle, be measured. This approach had the enormous advantage of being connected to a particle that was already known to exist and was already being studied intensively. Neutrinos were real. They were produced in enormous quantities in nuclear reactors and in the sun, and their mass was already a subject of intensive experimental investigation. If tachyonic behavior showed up anywhere in nature, the neutrino was one of the most plausible candidates. In the late 1970s and 1980s, several experiments measuring the tritium beta decay spectrum reported results that seemed, tantalizingly, to show a deficit of electrons near the endpoint, a slight concavity in the spectrum that was consistent with a negative mass squared for the neutrino. This was the tachyonic signature. The neutrino mass squared, calculated from these early data, appeared to be negative, which would mean the neutrino was faster than light. The physics community treated these results with a mixture of excitement and caution. They were not dismissed, the experiments were careful, and the results were reproducible, but they were also not accepted as evidence for tachyonic neutrinos without much more rigorous scrutiny. The concern was that the anomalous spectral shape might be produced not by a tachyonic neutrino mass, but by systematic experimental effects, unaccounted for energy losses, in the source molecular binding effects in the tritium decay, detector calibration errors, or any of a dozen other effects that could distort the endpoint shape and mimic a negative mass squared. The history of particle physics was full of anomalous results that had eventually been explained by systematic effects, and the community was rightly cautious about interpreting a spectral shape anomaly as evidence for faster-than-light physics. The resolution came gradually over the following decades as experimental techniques improved and the systematic effects were better understood and controlled. The most definitive answer came from the K-Tieren experiment, the Karlsruhe tritium neutrino experiment in Germany, which began taking data in 2019 after years of construction and represented the most precise beta decay endpoint measurement ever attempted. K-Tieren was specifically designed to measure the neutrino mass to unprecedented precision, using a massive spectrometer the size of a small building to analyze the electrons from tritium decay with extraordinary energy resolution. Its results showed no anomaly at the endpoint. The neutrino mass squared was consistent with zero or a small positive value, certainly not negative, certainly not tachyonic. The earlier anomalies were confirmed to be systematic effects. The neutrino, whatever else it might be, was not a tachyon. While the neutrino searches were proceeding, a parallel line of investigation was exploring the possibility of detecting tachyons through their electromagnetic radiation, a charged particle moving through a medium faster than the speed of light in that medium emitted Cherenkov radiation. The characteristic blue glow of nuclear reactors, by extension, a charged tachyon moving through the vacuum faster than the speed of light in vacuum, would emit Cherenkov radiation into the vacuum itself. This vacuum Cherenkov radiation would be a continuous emission. A tachyon would constantly be losing energy to radiation as it moved. In the same way that a charged particle moving faster than the local speed of light continuously emitted Cherenkov photons, the radiation would be detectable, in principle, as an anomalous source of photons with a distinctive angular and energy distribution. The absence of unexplained C and absence of unexplained C, Cherenkov-like radiation from the vacuum was another piece of negative evidence. More importantly, physicists realized that vacuum Cherenkov radiation from tachyons would have a self-limiting effect. A charged tachyon losing energy to Cherenkov radiation would, because of the inverted energy-velocity relationship, accelerate rather than decelerate. The energy lost to radiation would reduce the tachyon's energy, and reduced energy meant higher speed. The tachyon would emit more radiation, lose more energy, go faster still, emit more radiation, a runaway process that would quickly drive it to infinite speed. A charged tachyon, in this picture, could not persist at any finite speed for any appreciable time. It would almost instantly accelerate to infinite velocity, effectively removing itself from any possible interaction with ordinary matter. If charged tachyons existed, they would be self-erasing, created for an instant before disappearing into the infinite velocity limit, leaving no lasting trace in any detector. This self-erasing property of charged tachyons was one of the more elegant of the arguments for why tachyons, if they existed, might be undetectable. But it raised its own question. What about neutral tachyons? A neutral tachyon carrying no electric charge would not emit Cherenkov radiation, and would not undergo the runaway acceleration that erased charged tachyons. It might persist at a finite speed, traversing space without the continuous energy loss that doomed its charged counterparts. Neutral tachyons were, in some respects, more theoretically viable than charged ones, but they were also far harder to detect. A neutral particle that interacted weakly with ordinary matter and moved faster than light would leave almost no trace in any conventional detector. Its passage through matter would be largely invisible, its production in collisions unconfirmable, its existence inferred only indirectly if at all. The problem of detection was made still more acute by what some physicists called the transcendence argument, an informal name for a more rigorous observation about the nature of measurement. To detect a particle, you must receive some signal that it has been where it was. That signal, whether it is light, electromagnetic radiation of any kind, or another particle, travels at or below the speed of light. A tachyon, moving faster than light, would arrive at your detector before any signal announcing its impending arrival. More than that, after it had passed through your detector, the information that it had done so could only propagate away from the interaction point at the speed of light. If the tachyon moved fast enough, and its natural tendency was to move as fast as possible, it might traverse your detector and be gone before the causal consequences of its passage had time to propagate to your measurement apparatus. The detection event itself, the physical interaction between tachyon and detector, might be causally isolated from the readout electronics by the very speed of the tachyon. This was not a merely practical limitation. It had the character of a fundamental constraint arising from the structure of space-time itself. The act of measurement in relativistic physics was not instantaneous. It took time for the consequences of an interaction to propagate and be registered. A particle that moved faster than those consequences could propagate was in a very precise sense ahead of its own detectability. it was not merely difficult to detect. It was, in certain limiting cases, impossible to detect in principle, not because of any failure of experimental technique or instrumental sensitivity, but because the geometry of space-time placed its passage outside the causal reach of any measurement device operandi, anchored at or below the speed of light. Some theorists push this argument even further, suggesting that the fundamental framework of quantum measurement was itself incompatible with tachyons. Quantum measurement, in standard quantum mechanics, involved the interaction of a quantum system with a macroscopic measuring apparatus, leading to the collapse of the wave function and the registration of a definite outcome. This process was not well understood even for ordinary particles. It was the famous measurement problem of quantum mechanics, but it was at least formally well defined within the theory. For tachyons, even the formal framework broke down. Quantum field theory, the framework that unified quantum mechanics with special relativity and provided the mathematical description of all known particles, struggled to accommodate tachyonic fields in a way that permitted consistent measurement. The fields were unstable, the vacuum was ill-defined, and the propagators, the mathematical objects describing how quantum disturbances spread through space-time, had pathological properties that resisted physical interpretation. The most modern and sophisticated version of the undetectability argument came not from kinematic considerations or quantum field theory, but from the cosmological context. If tachyons existed as genuine physical particles, they should have been produced in the extreme conditions of the early universe, when temperatures and energies were high enough to produce every kind of particle that the laws of physics permitted. The early universe was, in a sense, the ultimate particle accelerator, a crucible of unimaginable energy density, in which all possible particle species should have been created in thermal equilibrium. If tachyons had been produced in the early universe, their subsequent behavior, their tendency to accelerate, their possible interactions with ordinary matter, their contribution to the energy density of the universe, should have left imprints in the cosmic microwave background, in the large-scale structure of the universe, in the primordial abundance of light elements. None of these cosmological observables showed any evidence of tachyonic contributions. The universe, examined at the largest scales in the earliest times, was consistent with known physics and showed no sign of a tachyonic sector. And yet, for all this accumulation of negative evidence, the hypothesis could not be definitively closed. Each experimental search had assumptions built into it, assumptions about how tachyons interacted, what charges they carried, what masses they had, how they coupled to the fields of ordinary matter. Change the assumptions and the experimental constraints might not apply. The tachyon that the neutrino experiments ruled out was a tachyonic neutrino with specific properties. The tachyon that the cosmic ray searches ruled out was a tachyon that was produced in atmospheric cascades and that carried enough charge or energy to leave a detectable trace. A tachyon that was neutral, that coupled to ordinary matter only gravitationally, that was produced only in processes beyond the reach of current accelerators, might slip through every constraint that had been established and remain hidden in a region of theory space that no experiment had yet illuminated. This was the uncomfortable position in which the search for tachyons rested. Not definitively excluded, not anywhere close to detected, but persisting as a logical possibility in the margins of physics. The detectors had been built, the data had been analyzed, the spectra had been measured, and the cosmic rays had been counted. The answer, every time, was nothing. And nothing, in the language of physics, was not the same as impossible. It was merely not found yet. The universe kept its counsel, and the tachyon, swift, imaginary, perpetually beyond the light barrier, and therefore perpetually beyond the reach of instruments that could only gather signals traveling at the speed of light or below, remained exactly where it had always been, just out of reach, just beyond the edge of the detectable. Forever, perhaps on the other side of a barrier that was not merely physical, but epistemic. A limit not just on how fast matter could travel, but on how much of reality the instruments of a slower-than-light civilization could ever hope to see. The universe does not always hide its secrets in darkness. Sometimes it hides them in plain sight, moving too fast to catch. There is a moment in the development of every great scientific idea when the language used to describe it changes. And that change of language turns out to be not merely cosmetic, but revolutionary. The history of physics is full of these moments, points at which a concept that had been described in one way was redescribed in another, and the redescription opened doors that the original framing had kept permanently closed. The shift from thinking about heat as a fluid, called caloric, to thinking about it as the kinetic energy of molecules was one such moment. The shift from thinking about gravity as a force acting across empty space to thinking about it as the curvature of space-time was another. And the shift from thinking about tachyons as particles, strange, faster-than-light particles with imaginary mass, flying through the universe in defiance of Einstein's speed limit, to thinking about them as something else entirely, as signals of instability in the fabric of quantum fields, was perhaps the most quietly profound reframing in the long and complicated story of faster-than-light physics. To understand what this reframing meant and why it mattered, it is necessary to understand something about the framework within which modern physics describes all the particles and forces that make up the observable universe. That framework is quantum field theory, and it is one of the most successful and most conceptually demanding structures that human beings have ever constructed. It begins with a deceptively simple idea. The fundamental constituents of nature are not particles, but fields. Fields that pervade all of space and time. Fields that exist everywhere simultaneously. Fields whose values at every point in space determine the physical properties of that region. Particles in quantum field theory are not tiny billiard balls moving through an otherwise empty arena. They are excitations of these underlying fields. Disturbances, ripples, quantized vibrations that arise when a field is excited above its ground state. An electron is not a thing that exists and moves. It is a localized excitation of the electron field. A photon is a quantized excitation of the electromagnetic field. Every particle in the Standard Model has a corresponding field, and what we call a particle is the quantum of energy in that field, the ground state of a quantum field. The state of lowest energy, the state the field settles into when left undisturbed, was called the vacuum. But the quantum vacuum was nothing like the empty, featureless void of classical intuition. It was a seething, fluctuating sea of virtual particles and fields, buzzing with quantum activity, even in the absence of any real excitations. The properties of the vacuum determined the properties of the particles that could be excited from it, and the most important property of all, the property that determined whether a field was stable or not, whether it described real physical particles or something else entirely, was the shape of the field's potential energy. Imagine the potential energy of a field as a landscape, a surface whose height at any point represented the energy cost of the field, having that particular value. A field in its ground state was like a ball resting at the lowest point of this landscape, stable, undisturbed, requiring energy to move. Small disturbances from this minimum, small excitations above the ground state, corresponded to particles. The energy of those particles, their mass, was determined by the curvature of the potential landscape at the minimum. A steeply curved minimum meant a heavy particle. A gently curved minimum meant a light one. A flat minimum, no curvature at all, meant a massless particle. This was the mathematical expression of a particle's mass in quantum field theory, and it connected the abstract geometry of the potential landscape to the concrete physical property of how much a particle resisted acceleration. But what if the landscape had no minimum? What if, instead of a valley, the potential had a maximum, a hilltop at the point the field was currently occupying? A ball in a hilltop was not in a stable equilibrium. It was in an unstable one. The slightest disturbance would send it rolling down the hill, away from the maximum and toward a lower energy configuration. A field sitting at a maximum of its potential was similarly unstable. It would not stay there. Any fluctuation, any perturbation, would cause it to roll toward a lower energy state, and the mathematical signature of this instability, the telltale sign, in the equations, that a field was sitting at a potential maximum rather than a potential minimum, was precisely an imaginary mass. This was the deep connection that quantum field theory revealed between tachyons and instability. When the equations of a quantum field theory produced a particle with imaginary mass, when the mathematics gave a negative value for the square of the mass, it was not, in the modern interpretation, a signal that faster than light particles existed. It was a signal that the field was unstable, that it was sitting at a maximum of its potential energy, that the vacuum of the theory was a false vacuum, a metastable state that would eventually, inevitably, decay into a true vacuum of lower energy. The tachyonic mode was not a particle to be observed. It was a direction in field space along which the field would roll, condensing from its unstable configuration into a new, stable one. The tachyon was the universe's way of saying, this is not the ground state, something is about to change. The most spectacular and consequential example of this tachyonic instability in all of physics was the Higgs field. The Higgs field was the last piece of the Standard Model to be confirmed experimentally, with the discovery of the Higgs boson at the Large Hadron Collider in 2012, a discovery that completed the theoretical edifice that physicists had been building since the 1960s, and that earned Peter Higgs and Francois Englert the Nobel Prize in Physics the following year. But long before that triumphant experimental confirmation, the Higgs field had been described theoretically in terms that were, at their core, tachyonic. The mechanism by which the Higgs field gave particles their mass was called spontaneous symmetry breaking, and it worked precisely through the kind of tachyonic instability that quantum field theory had taught physicists to recognize. In the very early universe, at temperatures above an enormous threshold, the Higgs field sat at a symmetric configuration, a field value of 0, at what appeared to be the minimum of the potential. At this configuration, the electroweak symmetry of the Standard Model was unbroken. The W and Z bosons, which carried the weak nuclear force, were massless, just like the photon. Quarks and electrons had no mass. The universe was a place of perfect symmetry and massless particles. But this symmetric configuration was not the true minimum of the Higgs potential. It was a local maxima, a hilltop in the potential landscape, stable only because the temperature was too high for the field to explore the shape of the potential beyond its immediate neighborhood. As the universe cooled, the field began to sense the true shape of the potential, and what it found was not a simple bowl with a minimum at 0. It was a shape that physicists described with the evocative name of the Mexican hat potential. A surface that was high in the center, fell away steeply to a circular valley, and then rose again. The field at 0 was at the top of the central bump, not at the bottom of the valley. And as the universe cooled through the electroweak phase transition, the field rolled off the central maximum and settled into the circular valley, the true vacuum, the true minimum of the potential energy. This settling, this spontaneous symmetry breaking, was the event that gave the universe its current structure. The Higgs field in the vacuum acquired a non-zero value, and this non-zero value interacted with the other fields of the Standard Model, giving the W and Z bosons their large masses, giving quarks and electrons their masses, breaking the electroweak symmetry into the separate electromagnetic and weak forces that we observe today. Everything about the structure of matter, the reason atoms were stable, the reason chemistry existed, the reason you and every physical object you had ever encountered had the properties it did, traced back to this phase transition, to the Higgs field rolling off a tachyonic maximum and settling into its true vacuum, Before the phase transition, the Higgs field at its symmetric configuration had a tachyonic mode. The curvature of the potential at the central maximum was negative. The field was at a hilltop, not a valley. And this negative curvature produced exactly the imaginary mass that was the signature of a tachyon. Had you tried to describe the excitations of the Higgs field around the symmetric configuration, you would have found a particle with imaginary mass, a tachyon. This was not a curiosity or a coincidence. It was the mathematical expression of the fact that the symmetric configuration was unstable, that the Higgs field was about to roll, that the universe was poised on the edge of a transformation that would change everything. The realization that tachyons in quantum field theory were not faster than light particles, but signatures of vacuum instability and spontaneous symmetry breaking transformed the concept from a speculative curiosity into a powerful and ubiquitous theoretical tool. Tachyonic fields appeared throughout theoretical physics, wherever phase transitions and symmetry breaking were relevant, which was to say, almost everywhere. In the theory of superconductivity, the effective field theory description of the superconducting phase transition involved a tachyonic mode that signaled the instability of the normal conducting phase. In cosmological models of inflation, the hypothetical period of exponential expansion in the very early universe, certain inflationary models involved fields that rolled off tachyonic maxima, with the tachyonic instability driving the inflationary expansion. In string theory, as noted before, tachyonic modes appeared in various contexts as signals of unstable string configurations undergoing decay. The whisper of the quantum field was this: every tachyon in the equations was a message, not a message about faster-than-light particles hiding in some inaccessible realm beyond the light barrier, but a message about the stability of the vacuum, about the true grau and state of the universe, about the transformations that fields underwent as they settled from false minima into true ones. The mathematics that Feinberg had interpreted as describing exotic particles was, in the deeper framework of quantum field theory, describing something more fundamental and more consequential: the dynamics of phase transitions that had shaped the universe at every scale. And yet the whisper had a second meaning, quieter than the first and more unsettling. The Higgs field in its current configuration was in the true minimum of its potential, or so physicists believed, but calculations performed in recent decades had raised a disturbing possibility. The parameters of the Standard Model, the measured values of the Higgs mass and the top quark mass, placed the universe in a region of parameter space that was technically described as metastable. The current vacuum might be a true minimum in the sense of being lower in energy than the symmetric configuration, but it might not be the absolute minimum. There might be another deeper minimum somewhere in field space, another lower valley, and the current vacuum might be separated from it by a potential barrier. If that barrier were ever breached, the universe would undergo another phase transition, another rolling of the field into a new configuration, another spontaneous symmetry breaking that would change the values of fundamental constants, the masses of particles, the structure of matter itself. The new vacuum would expand outward at the speed of light, a bubble of different physics consuming the old universe as it grew, with no warning and no remedy. The tachyon, in this context, was both a historical artifact and a future possibility. It had already appeared once in the electroweak phase transition of the early universe, and its appearance had been the mechanism by which the universe read the structure we inhabited. It might appear again, if the current vacuum was indeed metastable and the barrier to the deeper minimum was eventually breached by a quantum fluctuation. The whisper of the quantum field was a whisper about the past and a warning about the future simultaneously, written in the same mathematical language of imaginary mass and unstable hilltops. Point 6. Dark matter, the invisible majority. If the story of tachyons was a story about something that might not exist, the story of dark matter was something stranger still, a story about something that almost certainly did exist. that the evidence for was overwhelming and multiply confirmed, but that remained completely unknown in its fundamental nature despite decades of intensive experimental effort. Dark matter was not a speculative hypothesis, it was an observational fact in search of an explanation. The universe contained far more mass than the matter we could see, and whatever that extra mass was, it was unlike anything in the standard model, unlike anything detected in any laboratory, unlike anything in the catalog of known particles and fields. It was the invisible majority, more than 85% of all the matter in the universe. And it was, in its own way, as profound a mystery as anything that tachyons or faster than light physics had ever posed. The first serious evidence for dark matter came not from a particle physics experiment, but from an astronomical observation, and it came earlier than most people realized. In the 1930s, the Swiss-American astronomer Fritz Zwicky was studying the Coma cluster, a large cluster of galaxies lying several hundred million light-years from Earth. By measuring the velocities of the individual galaxies within the cluster, Zwicky could estimate the total mass of the cluster needed to gravitationally bind it together. The galaxies were moving fast enough that if the cluster contained only the visible matter he could observe, they should have been flying apart rather than remaining gravitationally bound. The cluster would have been unraveling before his eyes. The fact that it was not, the fact that it was a stable, bound structure, meant it contained far more mass than was visible. Zwicky called this missing mass dunkel materie, dark matter, and his estimate was that the visible matter he could observe accounted for only a small fraction of the total mass required. The rest was invisible. Zwicky's result was noted, filed, and largely set aside for decades. The technology of the time was not sufficient to pursue it definitively, and the astronomical community was not yet ready to accept a conclusion so radical on the basis of a single cluster measurement. The decisive turning point came in the 1970s, when the American astronomer Vera Rubin and her collaborator Kent Ford began measuring the rotation curves of spiral galaxies with unprecedented precision. A rotation curve was a plot of how fast stars orbited around the center of a galaxy at different distances from that center. In an ordinary gravitational system, like the solar system, the orbital velocity of objects fell off with distance. Planets farther from the Sun moved more slowly, in precise accordance with Kepler's laws and Newton's gravity. The same should have been true of stars in a galaxy. Stars far from the galactic center, orbiting in regions where most of the visible mass was interior to their orbits, should have been moving more slowly than stars near the center. What Rubin and Ford found was completely different. The rotation curves of spiral galaxies were flat. Stars at the outer edges of galaxies moved at roughly the same velocity as stars much closer to the center, and this pattern extended outward to the very limits of the detectable stellar population, showing no sign of the declining velocity that Newtonian gravity predicted. The only way to explain flat rotation curves within the framework of known gravitational physics was to suppose that galaxies were surrounded by vast halos of invisible mass that was not concentrated at the galactic center like the visible stars and gas, but extended outward in a roughly spherical distribution far beyond the visible disk. This invisible mass, this dark matter halo, provided the extra gravitational force that kept the outer stars moving at their observed velocities. Without it, the galaxies would have been flying apart, their outer regions unbound by the gravity of the visible matter alone. The confirmation came from multiple independent directions: gravitational lensing, the bending of light from distant objects by the gravity of intervening mass, provided a way to map the total mass distribution of galaxy clusters without any assumptions about what the mass was made of. When astronomers mapped the mass distribution of clusters through lensing, they consistently found far more mass than could be accounted for by the visible stars and gas. The discrepancy was not small. It was a factor of 5 or 6. The universe was overwhelmingly dominated by matter that emitted no light. absorbed no light, and interacted with ordinary matter only through gravity. The cosmic microwave background, the faint afterglow of radiation from the early universe, now cooled to just a few degrees above absolute zero and pervading all of space, provided yet another confirmation, this time from the very beginning of cosmic history. The tiny temperature fluctuations in the cosmic microwave background encoded information about the density perturbations in the early universe that eventually grew into the large-scale structure of galaxies and galaxy clusters. The fine, detailed pattern of these fluctuations was exquisitely sensitive to the composition of the universe, to the relative amounts of ordinary matter, radiation, dark matter, and dark energy. The precise measurements made by satellite experiments like WMAP and Planck fit beautifully with a model in which dark matter constituted approximately 27% of the total energy content of the universe, with ordinary matter, everything made of protons, neutrons, and electrons, every atom, every star, every planet, every living thing, contributing only about 5%. The rest was dark energy, the mysterious force driving the accelerating expansion of the universe. In this cosmic accounting, everything we had ever seen, or touched or measured, directly, was a thin scum on the surface of a much vaster, invisible reality. The question that this observational fact immediately posed was, what was dark matter made of? The evidence told physicists what dark matter did. It gravitated, it clumped, it formed halos around galaxies. It influenced the large-scale structure of the universe, but it said almost nothing about what dark matter was. The SOVs to almost nothing about what dark matter was. It did not emit light, which ruled out ordinary stars and gas. It did not absorb light, which ruled out clouds of ordinary dark material. It did not interact electromagnetically at all, which meant it carried no electric charge and felt no magnetic force. It interacted gravitationally. Of course, that was how it had been detected, and it might interact through the weak nuclear force, which was a much shorter range and feebler interaction. But beyond these constraints, its identity was completely open. The leading hypothesis for decades had been the WIMP, the weakly interacting massive particle. A WIMP was a hypothetical particle with a mass in the range of 10 to 1,000 times the proton mass, interacting with ordinary matter throughout the weak nuclear force and gravity, but not through electromagnetism. WIMPs were appealing for several reasons. They arose naturally in many extensions of the Standard Model, particularly in supersymmetric theories which predicted a whole family of new particles at higher masses as superpartners of the known particles. The lightest of these superpartners would be stable, prevented by symmetry from decaying into lighter particles, and would interact with ordinary matter only weakly. It was, in short, a perfect dark matter candidate, arising naturally from theoretical considerations independent of the dark matter problem itself. This coincidence, that theories developed for other reasons naturally produced particles with the right properties to be dark matter, was called the WIMP miracle, and it drove decades of experimental effort. Those experiments had been ingenious, sensitive, and ultimately, so far, unsuccessful. Underground detectors filled with ultra-pure liquid xenon, or germanium crystals, shielded from cosmic rays by kilometers of rock, waited for the rare collision between a dark matter particle drifting through the Earth and an atomic nucleus in the detector. The signature would be a tiny recoil, a nucleus nudged by the passing dark matter particle, depositing a minuscule amount of energy that the detector would register as a faint flash of light or a small ionization signal. Experiments like Lux, Xenon, Panda X, and their successors had pushed the sensitivity of these searches to extraordinary levels, ruling out WIMP interactions across a vast range of possible masses and interaction cross-sections. They had found nothing. The parameter space where WIMPs had been expected to live was largely excluded. The WIMP miracle was beginning to look less miraculous and more like a coincidence that the universe had declined to honor. The failure of WIMP searches had not killed the dark matter field, but had diversified it explosively. The community had spread out into a vast landscape of alternative candidates, each with its own theoretical motivation, its own experimental signature, and its own set of unanswered questions. Tachyons, extremely light particles originally proposed to solve a problem in quantum chromodynamics called the strong CP problem, had become one of the most actively pursued dark matter candidates. Sterile neutrinos, hypothetical cousins of the known neutrinos that did not interact through the weak force, or another, primordial black holes formed in the early universe before any stars existed, had enjoyed a resurgence of interest following the LIGO gravitational wave detections. Ultralight dark matter, fuzzy dark matter, self-interacting dark matter, asymmetric dark matter. The catalog of proposals had grown to encompass nearly every corner of theoretical possibility, each one a different answer to the same vast and stubborn question. The connection between dark matter and tachyons was not direct. There was no established theoretical framework in which the two were related, but they shared a kinship of epistemic condition that was worth sitting with for a moment. Both were things that the universe seemed to be pointing at, through its equations in one case, through its gravitational behavior in the other. Without allowing direct inspection, both had been searched for extensively without being found in the form expected. Both had been reinterpreted and reframed as the theoretical understanding had deepened, with the original concept giving way to something more subtle, more mathematically sophisticated, and in some ways more elusive. And both represented the same fundamental fact about our position in the cosmos, that the universe we could see and touch and measure was a small and possibly unrepresentative fraction of the universe that existed. The invisible majority was not an absence, it was a presence, vast, gravitationally consequential, structurally essential, that had been with us since the beginning, and that we were only beginning, in the most tentative and preliminary way, to learn how to read. The universe is not mostly what we can see. It never was. We are the exception, not the rule. Brief flames of visible matter in an ocean of the dark. There is something deeply disorienting about the possibility that everything you have ever seen, every star burning in the night sky, every galaxy wheeling through the darkness, every atom and every object you have ever touched, every atom and every object you have ever touched, every particle ever detected in every laboratory ever built, the entire luminous catalog of observable reality, amounts to less than 5% of what actually exists. That the universe you inhabit, the universe that science has spent centuries painstakingly mapping and measuring and describing, is a thin and possibly unrepresentative sliver of a much vaster whole. That the remaining 95%, the overwhelming majority of everything, is made of things so foreign to ordinary experience, so resistant to every instrument and method that science has developed, that after decades of intensive effort we still cannot say with certainty what they are. This is not a fringe idea entertained by speculative theorists on the margins of physics. It is the current, consensus, well-evidenced picture of the cosmos, supported by measurements of extraordinary precision from multiple independent lines of investigation. The universe is mostly dark, and we do not know what the dark is made of. The word dark and dark matter was chosen carefully. It did not mean black, in the way that a dark room was black or a dark sky was starless. It meant something more specific and more absolute. Dark matter was dark because it had no relationship with light whatsoever. It did not emit light. It was not luminous like a star or a glowing nebula. It did not absorb light. It was not opaque like a dust cloud or a molecular gas. It did not reflect light. It cast no shadows, scattered no photons, left no trace in any telescope sensitive to any wavelength of the electromagnetic spectrum, from radio waves to gamma rays. It was invisible not because it was too faint or too distant, but because it simply did not interact with light at all. the electromagnetic force, the force that governed every interaction between light and matter, that was responsible for every photon ever emitted or absorbed, that underpinned all of chemistry and therefore all of biology, was simply irrelevant to dark matter. It existed in a different relationship with the universe, one mediated only by gravity and possibly by the weak nuclear force, but otherwise sealed off from the electromagnetic world that made ordinary matter visible. Understanding why physicists were so confident that dark matter existed required understanding the nature of the evidence, which was not a single measurement but a convergence of independent observations from different scales, different epochs, and different methods, all pointing to the same conclusion. The story began, as many cosmological stories did, with a seemingly straightforward question about motion. When astronomers measured how fast things moved in gravitational systems, how fast galaxies moved within clusters, how fast stars orbited within galaxies, they found consistently and inexplicably that things were moving too fast, not a little too fast, dramatically, unambiguously too fast, fast enough that without additional invisible mass providing additional gravitational force, the systems would fly apart. They would not be bound structures at all. They would be dispersing clouds of unrelated objects rather than the coherent, gravitationally organized systems that observation clearly showed them to be. Fritz Zwicky encountered this problem first in the 1930s, measuring the velocities of galaxies in the Coma cluster, a massive collection of thousands of galaxies lying hundreds of millions of light-years from Earth. The visible mass of the cluster, estimated from the brightness of its member galaxies, was far too small to gravitationally bind the fast-moving galaxies he observed. The cluster should have been evaporating. It was not. Zwicky concluded that the cluster contained enormous quantities of invisible mass that contributed to the gravitational binding without contributing to the luminosity. He called it Dunkel Materie. The observation was correct and the conclusion was prescient, but the technology and the theoretical framework of the 1930s were not ready to pursue it, and Zwicky's dark matter lay largely dormant for 40 years. The resurrection came through the work of Vera Rubin, an American astronomer whose contributions to cosmology were transformative and whose recognition by the Nobel Committee, which never awarded her the prize despite the magnitude of her discoveries, remained one of the more glaring oversights in the history of that institution. Working with her collaborator Kent Ford in the 1970s, Rubin measured the rotation curves of spiral galaxies with unprecedented precision and care. The rotation curve of a galaxy was simply a plot of how fast stars and gas at different distances from the galactic center were orbiting, the orbital velocity as a function of distance from the center. It was a direct measurement of the gravitational field of the galaxy, and therefore of the distribution of mass within it. The physics of what to expect was clear. In any gravitational system where most of the mass was concentrated near the center, the orbital velocity of objects should follow a specific pattern, rising steeply near the center, reaching a peak, and then falling off with increasing distance from the center. This was exactly the pattern observed in the solar system, where the outer planets moved much more slowly than the inner ones, in precise accordance with the mass of the Sun concentrated at the center. The same pattern should have appeared in galaxies. The visible matter, the stars and gas, was concentrated in the bright central bulge and the disk, and beyond the edge of the visible disk, where there was little visible matter, the orbital velocities should have been declining. Kepler's laws, applied to the galactic scale, made an unambiguous prediction. What Rubin and Ford found was that the prediction was wrong, spectacularly, consistently, universally wrong. The rotation curves of spiral galaxies were not declining beyond the visible disk. They were flat. Stars and gas at the outermost detectable edges of galaxies were moving at essentially the same velocity as stars much closer to the center. Gravity was too strong at large radii, far stronger than the visible mass could account for. The only explanation that preserved the known laws of gravity was that the galaxies were surrounded by halos of invisible mass, vast, roughly spherical distributions of dark matter extending far beyond a visible disk, providing the extra gravitational force that kept the outer stars moving at the velocities Rubin measured. The rotation curves were not an anomaly or an error. They were a feature reproducible across galaxy after galaxy, a universal property of spiral galaxies that pointed unmistakably to the existence of something invisible and massive surrounding every one of them. The gravitational lensing of light provided an independent confirmation that required no assumptions about orbital dynamics. Einstein's general relativity predicted that massive objects would bend the paths of light rays passing near them. The more massive the object, the more pronounced the bending. This gravitational lensing had been confirmed dramatically in 1919, when the bending of starlight around the sun during a solar eclipse provided the first experimental test of general relativity. On cosmological scales, massive galaxy clusters acted as gravitational lenses, distorting and magnifying the light from more distant galaxies lying behind them. By measuring the degree of distortion, the shapes of the arcs and rings into which background galaxies were stretched by the lensing, astronomers could reconstruct the total mass distribution of the intervening cluster, independent of any assumption about what the mass was made of. The lensing mass was consistently and dramatically larger than the visible mass. Clusters that appeared, in optical and X-ray images, to contain a certain amount of visible matter in stars and hot gas, produced gravitational lensing effects that required 5 to 10 times more total mass. The invisible mass was not uniformly distributed. It was concentrated in roughly the same regions as the visible matter, forming halos around and between the cluster galaxies. But it completely dominated the total mass budget. The most spectacular single piece of evidence for dark matter from gravitational lensing came from the Bullet cluster, two galaxy clusters that had collided and passed through each other, caught in the aftermath of the collision by observations from the Chandra's X-ray Observatory and the Hubble Space Telescope. In the collision, the hot gas of each cluster, which constituted most of the visible baryonic mass, had been slowed by electromagnetic interactions, had piled up in the region between the two clusters, while the galaxies themselves had passed through relatively unimpeded. The gravitational lensing maps showed that the bulk of the mass in the system was not where the gas was, not in the central region where the electromagnetic interactions had concentrated it, but was traveling with the galaxies ahead of the gas in two separate clumps corresponding to the two colliding clusters. This spatial separation of mass from gas was the most direct evidence yet that the mass was not the gas, that it was something that did not interact electromagnetically, that had passed through the collision without being slowed by the interactions that had brought the gas to a halt in the middle. Dark matter, in the Bullet cluster, was not merely inferred from orbital dynamics or lensing statistics. It was, in a very direct visual sense, seen to be somewhere different from ordinary matter, behaving differently from ordinary matter, passing through the collision as if the other cluster were not there. It was a picture that made the reality of dark matter almost impossible to dismiss. The cosmic microwave background added the deepest layer of confirmation. In the first hundreds of thousands of years after the Big Bang, the universe was a hot side of thousands of years after the Big Bang. The universe was a hot, dense plasma of ordinary matter and radiation, coupled together in a fluid that supported acoustic oscillations, sound waves propagating through the primordial plasma. These oscillations left imprints on the temperature distribution of the cosmic microwave background. The faint pattern of hot and cold spots that space telescopes had mapped with extraordinary precision, the statistical pattern of these temperature fluctuations, specifically the relative heights of the peaks and troughs in what was called the power spectrum, was exquisitely sensitive to the composition of the universe. Ordinary matter and dark matter participated different, too, in the acoustic oscillations because dark matter, not coupled to radiation, behaved differently from the photon-baryon fluid of ordinary matter and light. The precise measurements of the power spectrum by WMAP and Planck fit with remarkable accuracy the predictions of a cosmological model in which dark matter constituted approximately 26% of the total energy budget of the universe. The fit was not approximate or qualitative. It was precise, matching the observed peak height to the level of percent-level accuracy. A universe without dark matter produced a completely different power spectrum, one that bore no resemblance to what was observed. So the dark matter existed. This was essentially beyond reasonable scientific doubt. But what it was remained completely unknown, and this was where the story became both fascinating and frustrating in equal measure. The constraints on dark matter's properties were extensive and well established. It was cold, moving slowly relative to the speed of light, because fast-moving dark matter would have smoothed out the density fluctuations that seeded galaxy formation, producing a universe with much less small-scale structure than was observed. It was collisionless, or very nearly so. It interacted with itself so weakly that dark matter halos could pass through each other in collisions, like the bullet cluster, without being disrupted or slowed. It was stable on cosmological timescales. It had been present since the early universe, and had not decayed into other particles. And it was electrically neutral. It felt no electrically force. These constraints were powerful, but they still left an enormous parameter space of possible identities. The leading candidate for decades had been the weakly interacting massive particle, a hypothetical particle with a mass somewhere between 10 and 1,000 times the proton mass, interacting with ordinary matter through the weak nuclear force and gravity. WIMPs were theoretically attractive for a reason that went beyond their dark matter credentials. Many extensions of the Standard Model, particularly supersymmetric theories, which proposed that every known particle had a heavier superpartner, naturally predicted the existence of stable, weakly interacting particles with roughly the right mass to be dark matter. If supersymmetry was correct, dark matter came for free, falling out of the theory as a byproduct of an independent theoretical framework. This coincidence gave the WIMP paradigm an intellectual appeal that drove experimental programs for 30 years. The searches were among the most technically demanding experiments ever constructed. Deep underground, shielded from cosmic rays by kilometers of rock that absorbed everything except the most penetrating particles, detectors filled with hundreds or thousands of kilograms of ultra-pure material waited for the infinitesimally rare event of a dark matter particle bumping into an atomic nucleus in the detector. The signature would be a nuclear recoil, a tiny, barely detectable kick delivered to a nucleus by the passing dark matter particle, depositing a few kiloelectron volts of energy as a faint flash of light or a small ionization signal. The Lux experiment, running in a former gold mine in South Dakota, and its successor Lux-Z, PL, used liquid xenon. The X-Enon experiments at Gran Sasso in Italy used the same approach. Handax in China, CDMS at Sudan, Coincheat. The list was long and the experiments were sophisticated, and the results were consistent. Nothing was found. The sensitivity improved by orders of magnitude. The parameter space shrank dramatically. The region where WIMPs had been expected to live was largely ruled out. The WIMP miracle was looking increasingly like a coincidence, say that the universe had chosen not to honor. This failure of WIMP searches transformed the field without ending it. The community spread outward into a vast and diverse landscape of alternatives. Tachyons, extremely light particles with masses billions of times smaller than the electron, originally proposed by Roberto Pecasi and Helen Quinn in 1977 to explain a puzzling symmetry of the strong nuclear force, became one of the most actively pursued candidates. Tachyons interacted with magnetic fields and could, in the presence of a strong enough magnetic field, convert into photons with a very specific energy. Experiments like ADMX, the Tachyon dark matter experiment, used superconducting resonant cavities immersed in powerful magnetic fields to search for the microwave photons that dark matter axions would produce if they pervaded the galactic halo and converted in the detector. The sensitivity had improved enormously in recent years, with ADMX and its successors probing the range of axion masses and couplings predicted by theory with increasing thoroughness. Sterile neutrinos, hypothetical counterparts to the known neutrinos that did not interact through the weak force and were therefore even more weakly coupled to ordinary matter, were another serious candidate. They could be produced in the early universe through mixing with ordinary neutrinos, and they would decay very slowly, occasionally producing an ordinary neutrino and a photon of a specific energy. In 2014, two independent teams of astronomers announced the detection of an unexplained X-ray emission line at an energy of 3.5 kiloelectron volts in the spectra of galaxy clusters and the Andromeda Galaxy, an energy that corresponded tantalizingly to the decay of a sterile neutrino with a mass of 7 kiloelectron volts. The signal was not large, and it was not universally accepted. Some analyses found it, others did not, and ordinary astrophysical processes could potentially explain it. It remained an intriguing anomaly rather than a confirmed discovery. Primordial black holes had their own renaissance. The detection by LIGO of gravitational waves from merging black holes with masses in the range of tens of solar masses prompted renewed interest in the possibility that some fraction of dark matter consisted of black holes formed in the early universe before any stars had ignited. These primordial black holes would carry no electromagnetic signature of their existence and would contribute to the gravitational mass of the universe in exactly the way dark matter was observed to do. The constraints on their abundance from gravitational lensing surveys and other observations ruled out primordial black holes as the dominant component of dark matter across most of the mass range. But windows remained open in certain mass ranges, and the possibility that they contributed a fraction of the dark matter could not be dismissed. Some physicists, confronting the persistent failure of particle dark matter searches, had begun to ask whether the problem lay not in the particle candidates but in the gravitational theory itself. Modified gravity theories, most famously modified Newtonian dynamics, or MOND, proposed by Mordechai Milgrom in 1983, suggested that Newton's law of gravity was modified at very low accelerations, producing the flat rotation curves observed in galaxies without any dark matter at all. MOND was remarkably successful at predicting galaxy rotation curves from visible mass alone, and its successes were genuine and not easily dismissed, but it struggled with galaxy clusters, with the bullet cluster and with the cosmic microwave background, in ways that were difficult to reconcile. More sophisticated relativistic extensions of MOND had been proposed, some of them quite recently, and the debate between particle dark matter and modified gravity remained genuinely open at the edges, even if the mainstream consensus strongly favored particle dark matter. The invisible majority remained invisible. After decades of searching, underground in space at particle accelerators, with gravitational wave detectors, and X-ray telescopes and microwave resonators, dark matter had revealed itself only through its gravitational effects, through what it did to the motion of visible matter and the bending of light, through the imprint it left on the structure of the universe at every scale. What it was in itself and its fundamental nature remained the deepest open question in all of astrophysics. It was the question that more than 5% of all papers in physics and astronomy touched on in some way. It was the question that had motivated the construction of some of the most sensitive and technically impressive experiments in scientific history. And it was the question that the universe, for all its mathematical tractability in other domains, had so far declined to answer directly. The dark matter sat out there in its halos holding the galaxies together, providing the gravitational scaffolding on which the visible universe had assembled itself, present since the beginning and essential to everything that had come after. It had made the existence of galaxies possible, had shaped the large-scale structure of the cosmos, had in a very real sense made the conditions for life possible by providing the gravitational wells in which ordinary matter collected and condensed, and eventually formed stars and planets. It was indispensable to the history of the universe, and completely unknown in its nature. It was the most important thing in the cosmos that science had never managed to identify. We live inside a mystery we cannot see, held together by forces we cannot name. In a universe that is mostly something we have never touched, science has always maintained two catalogs simultaneously. The first was the catalog of the known, the measured, the detected, the confirmed, the particles and forces and fields whose existence had been established beyond reasonable doubt by experiment, and whose properties have been pinned down with precision. This was the catalog that filled textbooks and won Nobel Prizes, the record of what humanity had definitively learned about the fundamental constituents of reality. The second catalog was quieter, less celebrated, and in some ways more interesting. It was the catalog of the should exist, the particles and entities that the mathematics of physics pointed toward, that arose naturally and sometimes inevitably from the theoretical frameworks that had been developed to describe the known world, that had every theoretical reason to be real, but had never been detected, never left a trace in any detector, never announced air, resonance in any experiment, despite searches of increasing sophistication and sensitivity. This second catalog was the hypothetical zoo, and it was populated by creatures of extraordinary strangeness. The zoo was not a collection of idle speculation or wishful thinking. Its inhabitants were not invented arbitrarily or conjured from nothing. Each one arose from a specific theoretical argument, a specific gap in the known physics, a specific asymmetry or inconsistency or incompleteness that the mathematics of the Standard Model or general relativity exposed, and that a new particle or field could resolve. The history of physics gave good reasons to take this catalog seriously. Antimatter had been a theoretical prediction before it was an experimental discovery. The neutrino had been proposed by Wolfgang Pauli as a desperate theoretical fix before it was detected. The Higgs boson was a mathematical necessity of the Standard Model for nearly 50 years before the Large Hadron Collider found it. Again and again, the universe had validated the theoretical imagination, had confirmed that the things the mathematics pointed at were real. The hypothetical zoo was populated on the assumption that this record would continue, that the universe, once more, had made the things the equations were asking for. The magnetic monopole was perhaps the oldest and most theoretically compelling resident of the zoo. It was also, in a certain sense, the most scandalous absentee from the catalog of known particles, because its absence was not merely puzzling, but constituted a deep and unresolved asymmetry in the laws of physics. To understand why, it was necessary to appreciate the profound symmetry that Maxwell's equations of electromagnetism almost had, but did not quite have. Maxwell's equations described the behavior of electric and magnetic fields with elegant completeness. They show how electric charges produced electric fields, how moving charges produced magnetic fields, how changing magnetic fields induced electric fields and changing electric fields induced magnetic fields. They were among the most beautiful equations in physics, and the foundation of everything from radio waves to fiber optics to the entire edifice of modern technology. But there was an asymmetry lurking within their beauty. Electric fields had sources, electric charges, the positive protons and negative electrons from which all electromagnetic phenomena ultimately derived. Magnetic fields did not. There were no magnetic charges in Maxwell's equations, no sources from which magnetic field lines emerged and into which they disappeared. Magnetic field lines had no endpoints. They formed closed loops. This asymmetry, sources for electric fields, no sources for magnetic fields, was not obviously wrong. It was consistent with every observation ever made. No one had ever found an isolated north or south magnetic pole. Every magnet ever examined, no matter how small, had both a north and a south pole. Cut a bar magnet in half, and you did not get a north pole and a south pole. You got two smaller magnets, each with its own north and south. The monopole seemed not to exist. Paul Dirac changed the theoretical status of the magnetic monopole in 1931 with a paper of breathtaking originality. Working within the framework of quantum mechanics, Dirac showed that if magnetic monopoles existed anywhere in the universe, even a single one, then electric charge would be quantized. Electric charge would come in discrete units, with every charge being an integer multiple of some fundamental unit. This was remarkable because charge quantization was an observed fact. The charges of the electron, proton, and every other particle were exact integer multiples of the elementary charge. No one had ever observed a particle with a charge of half or a third of the elementary charge. The quantization was precise and universal, and it cried out for an explanation. Dirac's monopole provided one. The mere existence of a single magnetic monopole somewhere in the cosmos would force electric charge to be quantized everywhere. Conversely, the observed quantization of charge was powerful indirect evidence that monopoles existed. Grand unified theories, the ambitious theoretical frameworks developed in the 1970s that attempted to unify the strong, weak, and electromagnetic forces into a single unified force at very high energies, made the monopole's existence not merely plausible but inevitable. In these theories, the unification of the forces at high energies implied a larger symmetry group whose spontaneous breaking at lower energies produced the separate forces we observed. And the mathematics of symmetry breaking in gauge theories, worked out by Gerard Hooft and Alexander Polyakov in 1974, showed that any grand unified theory necessarily produced magnetic monopoles as topological defects, stable, localized configurations of fields that could not be continuously deformed into the uniform vacuum. They were knots in the fabric of the unified field, impossible to untie. Their mass was enormous, roughly the mass of a bacterium, concentrated in a single particle, because it was set by the energy scale of grand unification, which was 16 orders of magnitude above the proton mass, and they should have been produced copiously in the hot, dense early universe, when temperatures were high enough to explore the grand unified energy scale. The problem was that they had never been found, not one, and their absence from cosmic ray detectors and monopole searches was not merely a null result, but a potential crisis for grand, unified theories. If monopoles had been produced, in the early universe in the quantities that naive calculations predicted, they should have dominated the energy density of the universe. There should have been so many of them that the universe would have collapsed long before galaxies could form. The absence of monopoles from the observed universe was one of several puzzles about the initial conditions of the cosmos that motivated Alan Guth's development of inflation in 1980, the proposal that the early universe had undergone a brief period of exponential expansion that diluted the monopole density to undetectable levels. Inflation solved the monopole problem by stretching the universe so rapidly that the monopoles produced at grand unification were spread across a volume so vast that the expected number within our observable horizon was less than one. The monopole's absence became, in this way, one of the evidential pillars supporting the inflationary picture of the early universe. A theoretical problem had become a cosmological clue. Dedicated searches for magnetic monopoles had been carried out using cosmic ray detectors, superconducting loops, sensitive to the change in flux that a passing monopole would produce, and analyses of ancient rocks and deep-sea sediments that might have captured monopoles over geological timescales. One experiment, the macro detector at Gran Sasso, ran for more than a decade looking for monopoles in cosmic rays and found none. The most famous near detection in the history of monopole searches was the Valentine's Day monopole of 1982, when a superconducting detector operated by Blas Cabrera at Stanford recorded a signal that was perfectly consistent with a magnetic monopole passing through the loop. The event was never repeated, never confirmed. and never explained. It stood in the literature as a single tantalizing, unverified data point, possibly a monopole, possibly an mental artifact, almost certainly the latter, but not definitively ruled out even today. The Tachyon was a resident of the zoo with a different pedigree. It had been proposed not to explain an astronomical observation or to satisfy a grand theoretical unification, but to resolve a specific and embarrassing inconsistency within quantum chromodynamics, the theory of the strong nuclear force. The inconsistency was called the strong CP problem, and it was one of the finest examples in physics of a small, precise observation carrying enormous theoretical implications. CP symmetry, the combined symmetry of charge conjugation and parity reversal, was a symmetry that most physicists had expected the strong force to obey. The mathematical structure of quantum chromodynamics allowed for a term in the equations that would violate CP symmetry, parameterized by a quantity called theta. This term was perfectly allowed by the theory. There was no obvious reason for it to be zero, and yet experiments measuring the electric dipole moment of the neutron, the degree to which the neutron's positive and negative charge distributions were offset from each other, had constrained theta to be smaller than 10 to the minus 10, essentially zero. The strong force obeyed CP symmetry to an extraordinary and unexplained precision. Why should theta be so small? There was no symmetry of the standard model that required it to vanish. It could, in principle, have taken any value between 0 and 2 pi. That it happened to be less than 10 to the minus 10 looked like a fine-tuning of spectacular improbability, the kind of coincidence that physicists found deeply unsatisfying, and that historically had always indicated a deeper explanation was waiting to be found. In 1977, Roberto Peccei and Helen Quinn proposed a solution, a new symmetry of nature that, when spontaneously broken, would dynamically drive theta to zero. The breaking of this symmetry would produce a new particle, a pseudo-Goldstone boson, that Steven Weinberg and Frank Wilczek independently identified and named the Tachyon. The Tachyon was extraordinarily light. Its mass was inversely proportional to the scale at which the Peccei-Quinn symmetry was broken. And if that scale was very high, the Tachyon mass would be tiny, potentially in the range of microelectron volts to millielectron volts. It was weakly coupled to ordinary matter, interacting primarily through its coupling to photons in the presence of magnetic fields. And it was stable on cosmological timescales. The realization that tachyons could also be dark matter came shortly after their theoretical introduction, and it transformed the tachyon from a solution to a particle physics problem into one of the most actively pursued dark matter candidates. Tachyons produced in the early universe through the misalignment mechanism, a process related to the initial value of the Peccei-Quinn field and its subsequent evolution, would be cold, stable, and present in roughly the right abundance to account for the observed dark matter density for appropriate values of the tachyon mass and the Peccei-Quinn scale. The theoretical motivation was thus doubly compelling. Tachyons solved an independent problem in particle physics and also provided a natural dark matter candidate. Experiments searching for tachyons using resonant microwave cavities in strong magnetic fields had been improving in sensitivity for decades, and the next generation of tachyon experiments, including ADMX, Haystack, Abracadabra, and a growing family of others, were beginning to probe the range of masses and couplings where theorists expected tachyons to be found. The sterile neutrino was perhaps the most minimal of the hypothetical zoo's inhabitants, requiring the smallest modification to the standard D model and motivated by the largest number of independent theoretical arguments. The standard model contained 3 neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino, each associated with one of the charged leptons. These neutrinos interacted through the weak force and were present in enormous quantities throughout the universe. The discovery of neutrino oscillations in the late 1990s and 2000s had established that neutrinos had mass, tiny masses, but non-zero, and this had been the first confirmed observational result that required physics beyond the standard model. The mechanism most naturally and most elegantly explaining why neutrino masses were so small was called the seesaw mechanism, and it required the existence of additional, very massive neutral leptons that did not interact through the weak force. These were the sterile neutrinos, right-handed counterparts to the left-handed neutrinos of the standard model, invisible to the weak force and therefore interacting with ordinary matter only through gravity and through mixing with ordinary neutrinos. Sterile neutrinos appeared in multiple theoretical contexts with multiple different masses and played multiple different roles. At very high masses, near the grand unification scale, they were the heavy partners required by the seesaw mechanism to suppress ordinary neutrino masses. At intermediate masses, in the kilo-electron-volt range, they were viable dark matter candidates, produced in the early universe through mixing with ordinary neutrinos and decaying slowly into ordinary neutrinos and photons, potentially producing the 3.5 kilo-electron-volt X-ray line that had been reported in galaxy cluster observations. At low masses, in the electron-volt range, they might explain anomalies observed in short Baseli neutrino oscillation experiments, where the observed rates of neutrino appearance and disappearance seemed inconsistent with the three-neutrino framework of the standard model. The reactor antineutrino anomaly, the LSND anomaly, the mini-Boone anomaly. A series of experimental results from neutrino experiments had accumulated over years, each individually ambiguous and disputed, but collectively suggesting that something was missing from the three-neutrino picture. Sterile neutrinos at the electron-volt scale could potentially explain these anomalies through additional oscillation channels not present in the standard model, but the picture was complicated and contested, with other experiments finding results inconsistent with the sterile neutrino interpretation, and the community remained divided on whether the anomalies were real signals or experimental artifacts. The micro-Boone experiment at Fermilab, specifically designed to test the mini-Boone anomaly with superior detector technology, had published results that were in tension with the light sterile neutrino interpretation, though the situation remained sufficiently complex that a definitive resolution had not yet been reached. Mirror matter was perhaps the most exotic and least experimentally constrained member of the hypothetical zoo, a proposal so far-reaching in its implications that it occupied a position somewhere between theoretical physics and science fiction, while remaining rigorously grounded in symmetry arguments of genuine power. The idea traced back to the fundamental question of parity symmetry, the symmetry between left and right, and its violation by the weak nuclear force. The discovery in 1956 that the weak force was not symmetric under mirror reflection, that nature had a definite handedness at the subatomic level, preferring left-handed neutrinos to right-handed ones, was one of the most shocking results in the history of physics. It meant that nature was fundamentally asymmetric between left and right, that a mirror universe in which all the weak interactions were replaced by their mirror images would be a different universe, governed by different physics. But parity was a symmetry of such naturalness and elegance that its violation was deeply unsatisfying to many physicists. Was there a way to restore it? Theoretical work in the 1950s and 1960s suggested there was, but the price was high. Parity could be restored as an exact symmetry of nature if the universe contained, in addition to all the ordinary particles we knew, an exact mirror copy of the entire standard model, a parallel sector of mirror particles, each one the parity-reversed counterpart of an ordinary particle. Mirror electrons, mirror protons, mirror quarks, mirror neutrinos, mirror photons, mirror quarks, an entire parallel periodic table of mirror matter, interacting among itself through mirror electromagnetic and mirror nuclear forces, but interacting with ordinary matter only through gravity. and possibly through a small number of portal interactions connecting the two sectors. A universe with mirror matter would, in principle, be exactly left-right symmetric. Every process in the ordinary sector would have a corresponding mirror process in the mirror sector, and the combined theory would be fully parity symmetric, even though each sector individually violated parity. Mirror matter would be dark matter, invisible to ordinary electromagnetic observations, contributing to the gravitational mass of the universe without contributing to its luminosity. If the mirror sector had roughly the same particle content and interactions as the ordinary sector, it might even contain mirror stars, mirror planets, and mirror life, a parallel world of ordinary complexity but electromagnetic invisibility, overlapping with our own universe in space-time while being almost completely decoupled from it. The observational constraints on mirror matter were extensive and came from many directions, but they were also model-dependent in ways that left significant parameter space unexplored. If mirror matter interacted with ordinary matter only through gravity, then its effects would be indistinguishable from those of any other form of cold dark matter, and the constraints from dark matter searches would apply but would not specifically confirm or deny the mirror matter hypothesis. If there were portal interactions, mixing between ordinary photons and mirror photons, or between ordinary neutrinos and mirror neutrinos, then additional constraints applied from precision measurements of those particles' properties. The experimental program for mirror matter was consequently less well-defined than for WIMPs or axions, because the predictions were more model-dependent and the signatures less specific. What all these inhabitants of the hypothetical zoo shared was a particular epistemic status, not quite real, not quite unreal, but hovering in the quantum superposition of theoretical prediction and experimental absence that defined the frontier of particle physics. They were real in the equations, real in the theoretical arguments, real in the sense that smart people had devoted careers to understanding their properties and designing experiments to detect them. They were absent from the experimental record in a way that was becoming increasingly constraining but had not yet reached the point of definitive exclusion. The space of possibility was shrinking, year by year, as experiments improved and sensitivity and theoretical understanding deepened. But the zoo still stood, its cages hypothetically occupied by creatures that left no tracks. The history of the zoo was a history of occasional transformative victories, moments when a hypothetical particle crossed the threshold from the second catalog to the first, from the should exist to the confirmed. The positron had made that crossing in 1932, the neutrino in 1956, the W and Z bosons in 1983, the top quark in 1995, the Higgs boson in 2012. Each crossing had been a triumph not just of experimental technique, but of theoretical imagination, a validation of the idea that the mathematics of physics was genuinely pointing at reality, that the equations were not merely describing the world as it was, but revealing the world as it had to be. The hypothetical zoo existed on the faith that this record would continue, that patience and ingenuity would eventually coax the remaining inhabitants out of hiding, that the universe had indeed made the things the mathematics was asking for, and was merely waiting for the right instrument, the right experiment, the right moment to reveal them. Whether that faith was justified remained the open question at the heart of modern particle physics. The LHC had found the Higgs but had found nothing else. No supersymmetric particles, no extra dimensions, no new forces or fields in the energy range it had explored. The dark matter detectors had grown more sensitive with every generation and had found nothing. The neutrino anomalies had remained ambiguous. The monopole searches had come up empty. The axion experiments were just beginning to reach the theoretically motivated parameter space. The zoo was full. The cages were built and the signs on each cage described the properties of the creature within in precise mathematical detail. The creatures themselves had not yet appeared. The universe owes us nothing, not confirmation, not clarity, not the satisfaction of finding what we are looking for. It keeps its own counsel, on its own schedule. In its own time, the zoo waits, the cages stand empty, and the mathematics, patient and indifferent, continues to end. Is that something is in there? There is a peculiar torture built into the practice of physics. It is not the torture of ignorance, of knowing nothing, of standing before a reality so opaque and featureless that no handhold presents itself, no pattern emerges, no question can even be properly formed. That kind of ignorance, total and undifferentiated, would at least have the mercy of not tantalizing. The torture of physics is more refined than that. It is the torture of almost knowing, of standing before a reality that yields just enough of itself to make the next layer visible, that offers just enough pattern to make the absence of the deeper pattern unbearable, that opens just enough doors to make the closed doors maddening. The universe, in its engagement with human inquiry, has always operated at precisely the boundary of the comprehensible, never so opaque as to defeat understanding entirely, never so transparent as to surrender its deepest nature without remainder. It has given us just enough rope to reach the ceiling, and then move the ceiling. This was not always obvious. In the late 19th century, there was a moment, brief, seductive, and in retrospect almost comically premature, when physics seemed to be approaching completion. The great edifice of classical physics had been constructed over 3 centuries of extraordinary intellectual effort. Newton had given the world its mechanics, its laws of motion, its theory of gravity. Maxwell had unified electricity, magnetism, and light. Thermodynamics had explained the relationship between heat and work. The periodic table had organized the elements. The kinetic theory had connected the macroscopic behavior of gases to the microscopic motion of molecules. The universe seemed, to many physicists of that era, to be a place whose fundamental laws were essentially known, whose remaining mysteries were matters of detail and precision rather than principle. The physicist Lord Kelvin, in a famous address in 1900, suggested that future physics would consist primarily of measuring known quantities to more decimal places. The great work, he implied, was largely done. Within 5 years, the entire structure had been overturned. The photoelectric effect and the blackbody radiation problem had revealed that classical physics could not describe the behavior of light and matter at small scales, and the resolution of those problems gave birth to quantum mechanics, a theory so foreign to classical intuition that its founders spent decades arguing about what it meant, and physicists are arguing still. The anomalous precession of Mercury's perihelion in the Michelson-Morley experiment had revealed that classical mechanics and the classical understanding of space and time were inadequate, and the resolution gave birth to special and general relativity, a transformation of the concepts of space, time, mass, and gravity so radical that it required an entirely new mathematical language to express. The 20th century opened with physics, seemingly complete, and ended with it incomparably deeper, incomparably more successful, and incomparably more aware of how much remained unknown. This pattern of apparent completion giving way to revolutionary incompleteness, of each answer generating deeper questions, of each door opened revealing a corridor of closed doors, was not unique to the transition from classical to modern physics. It was the persistent, structural character of physical inquiry at every stage of its development. The discovery of the atom seemed to explain chemistry, until the interior of the atom turned out to be an entirely new world of complexity. The discovery of the nucleus explained the atom, until the interior of the nucleus revealed quarks and gluons and the strong force. The Standard Model organized the quarks and leptons and force carriers into a coherent framework of extraordinary predictive power, until the discovery of neutrino masses and the existence of dark matter and dark energy made clear that the Standard Model was incomplete. Every resolution opened a new depth. Every answer was also a question, wearing a different costume. The philosopher of science might say that this was simply the nature of inquiry, that knowledge was an asymptotic approach to truth, forever getting closer without ever arriving. and there was something to that framing, but it did not quite capture the specific structural quality of physics, incompleteness, which was not random or uniform, but had a particular texture. The universe did not resist understanding evenly, the way a wall resists pressure applied uniformly across its surface. It resisted understanding selectively, in specific places, at specific scales, in ways that seemed almost to have been arranged. There were regions of reality where the theories worked with incredible precision, where predictions could be made and tested to 10 decimal places, where the match between theory and experiment was the most accurate in the history of science. And then, immediately adjacent to those regions of triumph, there were chasms of complete ignorance, the nature of dark matter, the reconciliation of quantum mechanics and general relativity, the origin of the matter-antimatter asymmetry, the value of the cosmological constant, the interpretation of quantum measurement. The universe was not uniformly mysterious. It was strategically mysterious, yielding here and withholding there in a pattern that maximized the sense of being forever on the verge of understanding without quite arriving. Consider the standard model of particle physics, the crown jewel of 20th century physics, the five framework that described the electromagnetic, weak and strong forces, and all their associated particles with a precision that had never been matched in any other field of science. The anomalous magnetic moment of the electron, calculated in quantum electrodynamics, agreed with experiment to 11 significant figures, a match so precise that it was equivalent to measuring the distance from New York to Los Angeles to within the width of a human hair. The predictions of electroweak theory for the masses of the W and Z bosons had been confirmed to better than 1%. The entire structure of the standard model had been tested repeatedly at every accessible energy scale and every accessible experimental configuration, and it had never been definitively wrong. It was, by any reasonable measure, one of the greatest intellectual achievements in human history. And it was obviously incomplete. It said nothing about gravity, the force most immediately familiar to human experience. The force that governed the large-scale structure of the universe was simply absent from the standard model. It contained 19 free parameters, numbers like the masses of the quarks and leptons, the strengths of the force couplings, the mixing angles of the neutrino sector, that had to be measured rather than derived, inserted by hand into the theory rather than falling out of it from deeper principles. It did not explain why there were 3 generations of quarks and leptons rather than 1 or 5 or 17. It did not explain why the forces had the strengths they had. It did not explain why the cosmological constant, the energy density of empty space, which general relativity allowed and observations confirmed to be small but non-zero, had the value it did, rather than a value 120 orders of magnitude larger, which was what naive dimensional analysis in quantum field theory predicted. That last discrepancy, the cosmological constant problem, was perhaps the single most dramatic example of the universe's habit of being almost understood. The cosmological constant was, in quantum field theory, the energy of the vacuum, the ground state energy of all the quantum fields that pervaded space. Every quantum field contributed to this energy, and when physicists calculated the contributions from known fields up to the scales accessible to current experiments, they obtained a number approximately 10 to the power of 120 times larger than the observed value. The observed cosmological constant was not zero. That would have been an easier problem, potentially explainable by a symmetry. It was a small but specific non-zero number, and explaining why it had precisely that value, rather than the enormous value that field theory naively predicted, or the zero value that a symmetry might impose, was a problem that had resisted every approach. The universe was expanding at an accelerating rate driven by dark energy, whose magnitude was the most precisely wrongly predicted quantity in the history of science. The calculation was spectacular in its accuracy of getting the wrong answer. The problem of quantum gravity was a different kind of strategic mystery, not a numerical discrepancy, but a structural one. General relativity, Einstein's theory of gravity, was a theory of space-time geometry, a classical field theory in which the gravitational field was the curvational four-dimensional manifold. Quantum mechanics was a theory of discrete, probabilistic, non-commuting observables, a framework in which the very concepts of smooth geometry and continuous fields had no obvious place. The two theories were the pillars of modern physics, each dominant and unrivaled in its own domain, and they were fundamentally incompatible. Combining them in the most straightforward way, treating gravity as a quantum field like the electromagnetic field, with a force-carrying particle called the graviton, produced a theory that was not merely wrong but mathematically meaningless, generating infinite answers that could not be removed by the renormalization techniques that had saved quantum field theory in other contexts. String theory and loop quantum gravity were the two most developed approaches to reconciling quantum mechanics and general relativity, and both had been pursued for decades by many of the most talented physicists of their generation. String theory had produced an extraordinary richness of mathematical structure, unexpected connections between different areas of mathematics, deep insights into the nature of black holes, the holographic principle suggesting that the information content of a volume of space was encoded on its boundary surface. But it had also produced in its landscape of possible solutions a number of distinct possible universes estimated at 10 to the power of 500, each with different values of the fundamental constants, and no obvious principle for selecting which one corresponded to the universe we inhabited. It had made no confirmed experimental predictions. Loop quantum gravity had taken a different approach, quantizing space-time geometry directly, and had produced insights into the quantum structure of black holes and cosmological singularities, but faced its own formidable mathematical and physical challenges. Neither theory had been tested, neither had yielded the clear, predictive, falsifiable framework that physicists hoped quantum gravity would eventually provide. Beneath these specific unsolved problems lay a more general and more philosophical puzzle, the question of why the universe was mathematically comprehensible at all. Why should the laws of nature be expressible in the lay nuage of mathematics? Why should abstract structures developed by mathematicians for purely aesthetic or intellectual reasons, Riemannian geometry, group theory, fiber bundles, complex Hilbert spaces, turn out to be precisely the right language for describing physical reality? The physicist Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences, and it remained as mysterious in the 21st century as when he wrote about it in 1960. There was no obvious reason why the universe should be mathematical. There was no obvious reason why human minds, evolved for the practical challenges of survival on a particular planet, should be capable of constructing the mathematical structures needed to describe reality at the quantum and cosmological scales. The match between mind and world at the level of fundamental physics was itself one of the deepest and most unresolved mysteries in the relationship between science and reality. And then there was the question that sat beneath all the others, the question that made all the specific unsolved problems seem like surface features of a much deeper mystery. Why were the constants of nature what they were? The fine structure constant, the dimensionless number that characterized the strength of the electromagnetic force, was approximately 137th. Why 137th? Why 137th, not 136? Not 138, but 137 to the precision currently measurable. The ratio of the proton mass to the electron mass was approximately 1836. The ratio of the gravitational force to the electromagnetic force between two protons was approximately 10 to the minus 36. These numbers were not predicted by any theory. They were measured and inserted into theories that took them as inputs, and they had to be extraordinarily close to the values they had in order for the universe to contain atoms, stars, galaxies, chemistry, and life. Small changes in the fine structure constant would destabilize atoms or prevent stars from burning. Small changes in the ratio of the cosmological constant to the matter density would either collapse the universe long before galaxies formed or expanded so rapidly that matter could never collect into structures. The universe appeared, from the perspective of its fundamental constants, to be extraordinarily finely tuned for complexity, for structure, for the emergence of the conditions that made observation and inquiry possible. This fine-tuning was not a solved problem. It was not even a problem with an agreed-upon framework for solution. Some physicists invoked the anthropic principle, the observation that the constants had to be compatible with observers existing to measure them, and that in a landscape of many universes with different constants, only those hospitable to observers would be observed. This was logically valid but explanatorily hollow, explaining why we observed what we observed without explaining why any particular set of constants was actualized. Some physicists believed that a deeper theory, the elusive theory of everything, would eventually derive the constants from first principles, showing that they could not have been otherwise, that the universe's specific character was a mathematical necessity rather than a contingent fact. This was a beautiful hope, but there was no evidence it was achievable, and the history of physics gave no guarantee that the constants were derivable rather than arbitrary. Some physicists suspected that the finely tuned constants reflected a selection effect in a vast multiverses, each with different constants, and that the apparent fine-tuning was no more mysterious than the fact that we found ourselves on a planet capable of supporting life, rather than on one of the vastly more numerous planets that could not. This was plausible but untestable, and an untestable explanation occupied an uneasy position between science and philosophy. What was striking about all of these responses to the fine-tuning problem was that none of them felt like answers. They felt like reframings, ways of relocating the mystery rather than dissolving it. The anthropic principle relocated it to the existence of the multiverse. The theory of everything hope relocated it to the future, to a calculation not yet performed. The multiverse argument relocated it to the existence and character of whatever mechanism generated the ensemble of universes. At each relocation, the mystery reconstituted itself, one level up, asking the same question in a new costume. Why this multiverse rather than another? Why these laws governing the generation of universes? Why any universes at all rather than nothing? The question of why there was something rather than nothing. The question of why there was something rather than nothing was perhaps the oldest and most stubbornly persistent question in human thought. Older than physics, older than physics, older than philosophy in its formal sense, present in every culture that had ever developed a cosmological tradition. Physics had approached it asymptotically for centuries. Getting closer in the sense of pushing the question further back in time, tracing the history of the universe to earlier and earlier moments, describing the conditions of the Big Bang with increasing precision, speculating about what might have preceded it. But the question itself had not been answered, and there were serious arguments that it could not be answered within the framework of physics as currently understood, because any physical answer to the question of why there was something rather than nothing would itself be a something. A law, a framework, a mathematical structure, whose existence would immediately regenerate the same question at the next level. The universe kept secrets not by being opaque, but by being almost transparent. Every secret it surrendered led to a deeper one. Every answer was a corridor. Every door opened onto a room with more doors. This was not a failure of science. It was science's fundamental and permanent condition, the condition that made it possible for inquiry to continue indefinitely, that ensured there would always be more to understand, that prevented the premature closure that had almost occurred in 1900, and that had been decisively refuted by the following century's revolutions. The universe was not waiting to be fully understood. It was structured in such a way that full understanding was not an achievable terminus, but an ever-receding horizon. Not because reality was arbitrary or random, or fundamentally inaccessible, but because the depth of reality exceeded any finite framework that a finite mind could construct to contain it. There was something to be found in this, not in frustration, but in a kind of reverence. The universe did not owe humanity its comprehension. It did not arrange itself for our convenience or scale its mysteries to our cognitive limitations. That it was as comprehensible as it was. That mathematics worked, that experiments could be performed and interpreted, that minds shaped by evolution for the demands of a biological environment could nonetheless reach toward quantum fields and curved space-time, and the origin of the cosmos was itself the most extraordinary fact about the relationship between consciousness and reality. Every equation that described nature accurately was evidence of something remarkable about the universe, that it had a structure, that the structure was consistent, that the consistency was expressible in a language that minds could learn, that tachyon might not exist. Dark matter might turn out to be something no one had yet imagined, the magnetic monopole. He might be hiding in a corner of parameter space that the next generation of experiments would finally illuminate. Or it might be permanently beyond reach, inflated away into a volume of space so vast that the nearest one was further away than the observable universe. The reconciliation of quantum mechanics and general relativity might come in a decade or a century, or might require conceptual revolutions not yet hinted at. The cosmological constant might eventually be explained, or it might remain the most precisely wrongly predicted number in science indefinitely. The questions would remain open or close and be replaced by deeper questions, in the pattern that had characterized physics for as long as physics had existed. But the inquiry would continue because the alternative, accepting ignorance, abandoning the effort to understand, deciding that the closed doors were permanently closed, was not actually available to minds constituted the way human minds were constituted. The drive to understand was not a luxury or a discipline. It was a fundamental feature of the kind of consciousness that had emerged in this universe, in this corner of space-time. Asking questions of the reality it found itself embedded in, the universe kept its secrets, but it kept them in a way that made the keeping itself a kind of communication. A signal that there was more, always more, that the depth did not bottom out, that the next layer was real even when it was invisible, that the corridor continued beyond every door. The questions that tachyons and dark matter and magnetic monopoles and quantum gravity and the cosmological constant and the fine-tuning of the constants all represented were not failures of understanding. They were the shape of the frontier, the edge where knowledge ended and the unknown began, the place where the light of comprehension met the dark of the not yet known, and produced the faint, tantalizing glow that had always drawn physicists forward. That glow was not diminishing. It was, if anything, brighter than it had ever been, because the instruments were more powerful, the mathematics was more sophisticated, the questions were more precisely formulated, and the outline of what was not known was drawn with greater clarity than at any previous moment in the history of science. The universe keeps its secrets, and in keeping them, it keeps us searching. And in keeping us searching, it keeps the most extraordinary conversation in the history of thought alive, the conversation between the mind that asks and the reality that answers, partially, provisionally, and always with the suggestion that the best question is the one not yet asked, waiting just beyond the door that is, as always, just slightly out of reach. We are not close to the end. We are not even close to the middle. We are exactly where we have always been, at the beginning of understanding, which is the only place understanding ever starts. You have traveled far tonight, faster than light, backward through time, into the invisible architecture of the universe itself. You have stood at the edge of what physics knows, and looked out into what it does not, tachyons that may never slow down. dark matter that holds entire galaxies together without ever being seen, particles that should exist, equations that point at something real, and a universe that keeps moving the horizon just as we reach for it. This is not a story of failure. It is a story of depth. Every mystery we explored tonight is evidence that reality is richer than any framework we have built to contain it. The universe is not withholding its secrets out of indifference. It is simply larger than the questions we have learned to ask. And now the questions can rest. Let your mind release the speed of light, the shape of space-time, the weight of invisible things. Let the equations dissolve. Let the corridors close gently, one by one, until there is only the quiet. You do not need to solve anything tonight. The monopoles will still be missing tomorrow. The dark matter will still be dark. The tachyons will still be racing through their faster-than-light world, indifferent to whether we have found them or not. The universe has been keeping its secrets for 13.8 billion years. It can keep them a few more hours while you sleep. Rest now. The cosmos will still be waiting, vast, patient, and full of questions, when you wake.